Welcome back to Gruber Motor Company. I'm Pete Gruber.
I'm Mark Schaffner. Good afternoon and welcome to our special podcast of the Tesla Investor Day.
And we are waiting for Elon and company to come live. We're going to express some opinions. We've had a little bit of feedback from TikTok a few minutes ago. A lot of curiosity about this Model 2 vehicle, which if it is a sub $25,000 EV, could really begin to increase EV adoption rate tremendously.
Most definitely. We've been debating on how long it might take for a new model to come out, and one of our TikTok viewers, Smuggler, has been talking back and forth with us a little bit. He says that on the Tesla Model 2, he'd guess about 2 years. The truck is the delay. Mm-hmm. I think that's a good point, Smuggler. I do think the truck is the delay. Considering their past history, where they announced the Model 3 and it came out 5 years later, they announced the truck and it came out, it's 5 years and counting. I wouldn't be surprised if it's even longer than 2 years.
TikTok, Brentwood Barbecue from Toledo, Ohio says, hi there, welcome.
Welcome, Brentwood.
You want to mention that he also followed us as well, so thank you for the follow.
Thank you very much.
Want to take a picture of you guys real quick?
All right, we're getting our thumbnail picture taken here.
Hey, 3, 2, 1. There, got it.
So the background behind us while we're waiting, this was actually an event out at the Scottsdale Air Park that I went to. And it was an exotic car event, but we don't see too many cars here at least. They actually had pretty young ladies hanging from the ceiling doing acrobatics.
Oh my
There were
gosh.
at least 3 or 4 of them. And it was amazing. They were up about 12 feet or so, and their ability and agility to move around these parallel bars, or what are the ones that are hanging with the loops? I forget what those are called, but that's what they were using.
You know the loops?
Loops, yeah, like round metal loops, and pull themselves up, upside down, and it was just amazing. The strength, I mean, their upper body strength had to be tremendous. TikTok, Maple Leafer from Canada. Okay, Model 2, hopefully it'll be an inner city model.
And Marvin Sliver from YouTube Shorts says, hi there. Hi, Marvin. Glad to have you on.
Very important question coming up here from Smuggler.
TikTok, Smuggler, why don't you have girls dancing on poles behind you? You might get more views. Ha ha, he's probably right.
Jesse, you're going to have to import the girls.
Investor Day started.
Okay, let's go to Investor Day then.
Starting, so we're going to switch over.
Okay.
1 second, I'm going to switch you guys right now.
We also talked a bit about stock usually goes a bit lower during these investor days, and we don't know whether it's the lack of dynamic people up on the stage at Tesla, or whether it's just something that happens during these kinds of announcements, because people don't know what direction they're going to take.
So as we reflect back
Can we get audio?
on the history of the company, there's been distinct phases of product advancement, technology innovation, and rapid
And I can't
volume
see who
growth.
that is. Is that Drew
The
Baglino?
most recent of which has been the global expansion and localization of the Model Y program. And so
Probably bring
today,
that up on my
we want to
computer
talk
here.
about the future. We don't want to talk about this quarter or next quarter. We want to go further out into the future. And we've divided today's presentation into 3 parts. The first
I
of
think
which
everybody's having
we're going to
technical
go
issues
macro.
with this.
What does it take to convert Earth to
There we go.
sustainable energy generation and use? The second, we want to talk about Tesla's contribution to that global need. And we're going to go function by function through the company, and you'll meet our entire leadership team, and we're going to get into the details of what those teams are doing as part of the broader goal. And then in the third part, we're going to bring it back up and talk about what this all means for the company as a whole. So before we get started, statements made in this presentation are forward-looking statements that are subject to risks and uncertainties. More details can be found in our written materials. So with that, let's get started. Part 1, Elon Musk and Drew Baglino.
So it is Elon and Drew. Okay.
Okay. By the way, I happen to really like Smuggler's comment back to KC.
All right,
Okay.
master plan part 3. So,
That is a good one,
as,
Smuggler.
Zach was mentioning, the thing that I think is we wanted to convey, probably more importantly than anything else that we talk about here, is that there is a clear path to a sustainable energy Earth. It's not, it doesn't require destroying natural habitats. It doesn't require us to be austere and stop using electricity and sort of be in the cold or anything. The story, and I think that this holds together quite well, and we'll be actually publishing a detailed white paper with all of our assumptions and calculations, is that there is a clear path to a fully sustainable Earth with abundance. In fact, you could support a civilization much bigger than Earth, than much more than the 8 billion humans, could actually be supported sustainably on Earth. And I'm just often shocked and surprised by how few people realize this. Most of the smart people I know actually don't see this clear path. They think that there's not a path to a sustainable energy future, or at least there's not one that is sustainable at our current population, or that we'd have to resort to extreme measures. None of this is true. So we're going to walk through the calculations for how to create a sustainable energy civilization.
they're going to hear it.
Okay.
Most of the smart people I know actually
And to set the stage, today our energy economy, let's be honest, it's dirty and it's wasteful. Over 80% of global energy, primary energy, comes from fossil fuels, and only 1/3 of that global energy actually ends up delivering useful work or heat. This is the problem statement, but we're here to talk about the solution.
Yeah, it's like some of this I'm going to elaborate because there's a very wide range of technical expertise out there, from people who are like, whatever, level 9 wizards in this subject, to people who do not do engineering.
For those of you that are viewing on TikTok,
If you have a guess,
I know that you're having some problems probably hearing the actual YouTube presentation on Investor Day.
often maybe only 25% of the
I do wish we could do a split screen like Smuggler has suggested on TikTok, but we're not there technologically yet. I would encourage you guys to go over to YouTube to view the Investor Day as well, and to our YouTube channel you could see us as well as the people on YouTube.
When you look at all that, for a
Good
typical
point.
gasoline car is actually going to be using less than 20%, fully considered, of the energy from the oil actually goes into motion. So this is when we see people doing calculations for what does it take to create a sustainable energy Earth, they assume that the same energy amount is required for an electrified civilization versus a combustion civilization. This is not true, because most of the energy of combustion is waste heat.
And even to get the fuel to combust in the first place and get it to the end use, there's a lot lost along the way. I mean, this is the primary energy consumption, 165
Do you
petawatt
think you're
hours
going
a
to go
year.
into what
Petawatt hour
is
is
the
a
energy
trillion
waste if only
terawatt-
1/3 of
trillion
energy is
kilowatt
going
hours, so
to
it's a large amount
is
of
currently
energy.
being
But the nice
used?
thing about electrified economy
I don't know.
Two-thirds is being wasted.
there's a better way.
It
to talk
looks
about
like
it,
it's going to be a
is that
very technical
through end-use
beginning
efficiency and
to this
through
Investor
efficiency
Day.
along every step of the way. Actually, the total energy use halves. So this is one of the most enabling aspects of electrifying everything, is that the sustainable energy economy is that much easier to accomplish. It's actually half the problem statement of the fossil fuel economy.
Yeah, and we're being conservative here, so it could be better than half, but we're trying to have assumptions that are reasonable, not overly optimistic, in fact slightly pessimistic. So it's really better than half, but just say it's easy to make the argument that we need half as much energy with an electric economy versus a combustion economy.
Yep.
You know, for Richard and Jesse,
So how the master plan works.
do you think it would be
yeah.
too disruptive if we were to turn on the closed captioning?
that is needed at very large scale that is not currently present is a vast amount of battery energy storage. Our rough calculations are that this is about 240 terawatt hours, or 240,000 gigawatt hours.
I see that fine.
This
How
is
about
a
you,
lot of
Pete?
batteries, but it is actually a very
The closed
achievable
captioning
amount.
that's up there, just like
Yeah.
you have on
We'll
here.
go into details
No,
on
you
that.
got better eyes than I
So,
do. I didn't realize
That's
that.
a combination of vehicles and
I have it
stations.
here, but there's a
So
delay.
You've got solar or wind, you've got to store the energy when the wind is not blowing, the sun is not shining. And so we're seeing
Pete?
sort of an 8 to
I'm
1
going to just ask a
ratio
question here
of,
as well. Are you getting a kickback from Google?
stored energy
You seem to have that hat on every
So
time.
30
Oh, the
terawatt
hat
hours of power.
actually,
But
my
it's also
daughter
30 terawatts of power.
subcontracted for them years ago, and they gave the subcontractors these
Capital
hats.
expenditure calculation for
It's one of my warmer
manufacturing
hats, so
investment
that's
is
why I like
more
wearing
like,
it.
6 trillion, but we made it higher.
I guess eventually we'll have to
10
do
trillion.
product
And
placement,
this
though.
is across
I think eventually
mining,
we will.
refining, battery factories, recycling, vehicle factories, all the things that we're going to talk about needing to invest in to build the sustainable energy economy.
Yeah. Now, if you look at the total world economy, it's just under 100
Now,
trillion.
both of these guys
So if this was
were
spread
in an
out,
Investor
say, over
Day
10
type
years, it would
presentation
be
a year or so
1%
ago,
of the global
Okay.
economy.
both Drew and
Over
Elon.
20 years, it would be
And,
half a
yeah, it
percent
did start
of
out
the
very
global economy.
technical as
So
well.
This is, not a big number relative to the global economy. As Drew mentioned, you need about half.
I
as
do
much
think it's
energy
notable how
with
they're
electric
making
economy
the
versus
case that
combustion
a
economy. And
global
in terms of
sustainable
what it's like,
economy
how much land would be
is
used,
completely
it's
achievable.
Less than 0.2%.
There are a
of the
lot of
land area
environmentalists that are out there that say that in order
Like,
to
people don't realize quite
preserve
how
and
much
protect
energy
our
is reaching us from the
planet
sun.
and environment,
It's roughly
that
a
we have to
gigawatt per
dial
square
back our
kilometer.
energy usage at all costs.
And
Even
that's
going
trackable
to the
time,
point
but it's,
of only
if you
driving
multiply
smaller
that
electric
by,
cars.
say,
Mhm.
4 to get the continuous power.
We'll squeeze in a quick question. Instagram,
That gives you the
Thia
luxury of
Lear,
solar. And you can put wind and solar all in the same
mods_services
place.
says hi.
In a lot of places that currently
Welcome.
have wind, you could have solar there and double
And
the
Smuggler
energy.
says the next thing I'll
wind
be doing is
offshore.
putting a Pepsi can on the table.
Wind is even more flexible.
It depends on how much they pay us, I guess.
So Earth is
But I do have my Gruber
the point
thermos.
is that,
Yeah, we
Which,
can put that up on the table.
pretty,
Yeah.
really a remarkably small amount of Earth's land area, we can go fully sustainable. Yeah.
And from do the resources and raw materials exist to support this transition? We'll go through that in detail, but we do not see any insurmountable resource challenges at all. In fact, in the end, we should be mining less ore to accomplish this economy than we currently do with the fossil fuel economy, and we're going to talk through that.
Yeah, just to emphasize that again, the electrified economy will require less mining than the current economy does.
Yes.
Less, not more. Okay.
So this is the plan, and now we'll get into a little bit more of the details of the plan. Basically, 5 areas of work. First, renewably power the existing grid. Second, switch to electric vehicles. Third, switch homes, businesses, and industry heating to heat pumps. Fourth, high temp heat delivery and storage for high temp industrial and chemical processes, and a little bit of green hydrogen in there for chemical processes that need hydrogen. And finally, sustainably fuel planes and boats. These are the 5 areas, and we're going to go into detail on all of
Well,
them.
this is really breaking new ground for
My
us.
opinion is that as we
Our
improve the
normal
energy
production
density
doesn't
of
include this
batteries,
level of
you'll see
complexity.
all transportation,
Yes.
Go fully electric, with the exception of rockets. That's awkward. But you can make the fuel with CO2 and water.
Well, let's
So
get
you
a
can
few
make methanol with
questions
CO2 and water.
out of the
So,
way here.
In fact,
Do
that's
that
From
with just
Outback
electricity.
EV Hunter from
exactly.
YouTube. For your information, this would be a good
fact,
time
on
for a
Mars,
morning show for us in
I'll get there
Aussie.
at some point.
Maybe you could call this the afternoon show.
CO2 and there's
Good
water
point.
ice.
Outback EV Hunter, we were just talking about that a couple minutes ago.
Turn that into
You're
CO4,
exactly right.
methane, and oxygen.
I assume it's probably about 7 o'clock in the morning there on Thursday morning.
And Europe is asleep right now.
So first,
Smuggler says I can't hear
repowering
the
existing
audio.
grid with renewables, and this is going to be a consistent theme. You'll see our estimates for the number of
Okay, they're working on it.
terawatts and trillions of investment at the bottom of the page. This is already
Is it us they
actively
can't hear or
in front
the
of us.
presentation?
60% of the generation added to the U.S. grid
Okay,
was solar in
all right.
2022. And actually, on a year-on-year basis,
Okay.
solar deployment is growing 50% year on year as of 2022. So this is a serious upswing, and if we continue this trend, this is going to be behind us before we
Okay.
know it.
So TikTok guys
Second,
need to go
switching
to
to
the other
electric vehicles.
platform.
Again,
YouTube?
21% reduction in fossil fuel use by doing this alone.
Okay. Oh, even
Obviously,
Facebook.
Tesla is heavily engaged in this
LinkedIn,
activity.
there we
as
go.
along
Got a
with
few.
many others.
All right, we-
Overall, EV production grew 59% year on year in 2022.
So we got Mark coming in. He says, we still live in a capital
10%
economy
market
and
share.
product
It's an
endorsement and marketing are
awesome
key
milestone.
to many business
super
models,
excited
right?
to see that.
That's right.
Yeah, I mean, this is
So I have an observation to make here.
happening
I'm watching
very
Elon and Drew up on stage, right?
and I mean,
And I don't know if you've noticed, but lately Elon is wearing a lot of suits.
electric,
He's got some legal issues to contend with, and you know that's the appropriate costume for a courtroom: suit, shirt, tie, that sort of thing. So I thought he was going to continue with that new look up here on stage, but he's back to his old black T-shirt. The only thing that he's not doing, him and Drew, they both have black T-shirts. They don't have any sunglasses, so we should reach out to them and explain to them that this would probably help their presentation.
Probably would help a lot.
Really much of those benefits at all in this number. And what does this fleet look like? You know, just
He's talking about
rough
repowering
view
the existing
from
grid
our
with
perspective. Of course, this
renewables.
could be wrong, but you know,
And that was one of the things that we
you
were
can see the sort of
suspecting they
breakdown of
will
the
talk
45
about
electric
is
vehicles.
stationary power and
our
the
goal
potential
is
for
to
Tesla
do 20
to sell
million
power,
electric vehicles a year.
become a utility, in other words.
fewer vehicles
Look at
will be
the
needed with
graphic
passenger
that's going to be
vehicles,
coming up. Some people are
with
saying
autonomy.
already
So
the potential for not one, but possibly
debate as
two
to
new
what that number
vehicles.
is, but it's
Okay, I
some
did
number
not
less
see
than
that.
Number of vehicles.
You're
on
going to
my
see it
screen.
come
Roughly
up here
2
on your
billion
local
cars and
computer.
trucks
Looks like we have a lag here.
There's a big delay,
operational
yeah.
in the world today. And
Yeah, so what we show here is actually, I think, only 1.4 million or so. So
this is their
we're
existing
representing
lineup
1.4
here.
billion, I mean, or so. So a smaller fleet.
SX3Y.
And you know, the numbers here in this presentation are around 85 million vehicles a year produced, just to give you a sense.
We
of
know
how
that
we're
this
thinking
is a
about this.
very
Again, we're
new
gonna put all these
platform or a
assumptions
new
up on
type of thing
you know,
for us at
people's
this
thoughts.
point.
yeah. So
Best thing we can ask actually is if the audience
so we're
you
basically
guys can
heading
cooperate
rapidly
with this
towards
as well.
electric or
If you're having any audio issues or other technical issues, send us a
And
comment.
one of the reasons why EVs
The
are so
guys in the
enabling
back
is
are
this
wanting to take a
end-use
look at it and make
efficiency
sure that
point.
things are working okay.
Tesla Model 3, it's 4 times more efficient from the well to wheel than
Smuggler,
Toyota
thank you.
Corolla.
He says
That's all
he just
about
got us to
efficiency of
3,000
getting
likes.
The electricity into the car
Thank
in a
you,
sustainable
Smuggler.
energy economy, and then how efficient the car is in transferring
And thank you,
that
Mark.
stored,
Audio on YouTube is
energy
fine
to
for 'em.
motion on the road.
Okay.
When compared to the
On
engine in
YouTube.
the Toyota Corolla and all the extraction, refining, transmission, distribution of the gasoline to the Toyota Corolla. And just for, this is a fun reference, Model
we
3
go.
can drive over a mile on the energy it takes to boil a pot of water for pasta, and then it can drive another mile on the energy it took to cook the pasta. And that pasta is 1 pound, and Model 3 is like 4,000 pounds. Just to give you a sense of just it really doesn't use a lot of energy to move a Model 3, that 4,000 pound object, down the road.
Yeah, also, heat is a lot more energy than motion.
Did he just talk about cooking pasta?
He did.
But people,
I'm hungry now.
boil a pot of pasta, you don't even think about it.
Oh,
It's just interesting how efficient.
he's
these
talking
are.
about the
Next,
amount of energy it
switching to
takes
heat pumps in homes, businesses, and
to
industry.
power a Model 3 is
You
equivalent
know,
to
right now heat
energy
pumps
to
meet
cook
10%
a
of
pound of
building heating
pasta.
needs.
Oh, okay.
Install rates growing 10% year on year. It really needs to accelerate. Heat pumps can serve, heat applications up to 200 C in businesses and industry. And from an investment perspective, as you can see on this page, this is actually the lowest hanging fruit in terms of displacing fossil fuels. You might be saying, well, what exactly is a heat pump? So,
Here in Phoenix, we take
heat
that for
pumps don't move
granted.
heat, don't
Virtually
create
all
heat,
new homes that are
they
built
move
in
heat.
Phoenix have heat pump
When you
technology.
think about
Right.
the natural gas
We're
furnace
kind of
in your
unique in the
house,
rest of the United
it is
States
generating
because
heat
heat
itself,
pumps
but
are
what the heat
actually
pump is doing is
very
actually moving heat
uncommon
from outside
elsewhere.
of your house into your house.
Where there's
They're
a
just an
cooler
air
climate,
conditioner
where it's
or
freezing
refrigerator
temperatures on a
in
regular
reverse.
basis,
So we're
heat
surrounded by
pumps
heat pumps.
typically
There's
don't exist.
they're all over this factory.
That's
they're
one
in
of the
your
reasons
house.
we have problems with our
And all
commercial
this really
buildings
is
when it
about
gets very
bringing
cold
them
outside.
to displace all the fossil
We have
fuel
all
heat
heat pumps in
heating
these
all the
buildings,
homes
too.
in the industry that we can.
So there are some
And
unique
from an energy
problems with the
efficiency
heat pumps when they
perspective,
get
it's a
cold, but they are
three
still
times
much more
reduction in
efficient
the
in the
total
way that they
energy
use
required to
energy
heat these
overall than most other
It's a
types
real
of
obvious
heating.
thing to do.
Yeah, heat pumps. They're in our cars, now as default.
What,
and at some point,
What
we might make
platform are you
heat
guys
pump
streaming this?
maybe.
this investor day from? Because mine has a real serious delay and I'm on
Next, a little bit
YouTube.
more detail on electrifying high temp sort of
Yeah.
industrial chemical processes. So over 50%
Yeah,
of
way
industrial heat
behind.
is greater than 400 C. Where, cement,
Yeah.
steel, fertilizers, chemicals, plastics, metals refining all need like 1500 C. So we need a solution here. Ultimately, it's purpose-built equipment that enables electrification. Carbon graphite is stable up to 2800 C.
Oh.
There's other options in the 1500 C range, like silicon carbide.
Ah,
other
thank you.
materials. So the idea here is
That's
you
why we
create
have technical
and store
experts.
heat when
Yes.
renewable power is available.
I'm
This
seeing
is
exactly
sustainable
what's on the
energy
screen now.
economy.
Okay,
Mundo
there we go.
Finance, welcome
renewable
from
energy is
Brazil.
intermittent.
Glad to have you
Peak of
on.
the day, you've got more generation than you need. You make a bunch of heat then, and then you transfer that heat into the industrial process 24 hours a day using the stored heat you created when the sun or the wind is blowing. That's the concept here. And then on the hydrogen side, we also need green hydrogen to decarbonize metals and chemical refining processes.
that better?
This is things like ammonia, making steel. There's roughly 120 million tons of hydrogen sourced from fossil fuel today to do these things. And hydrogen can also directly replace coal, which is currently used in a ton of steel production.
Well, at least
through
the
a process called directly reducing iron.
captioning
to
now
replace
matches.
blast furnaces with a hydrogen reducing direct reduced iron furnace. And this is the way to eliminate fossil fuels from these aspects of the economy and the CO2 associated with them.
Yeah, so I mean, some of this, there's like room to disagree, but some amount of hydrogen is needed for industrial processes. My personal opinion
It's going
is
to be
that
kind of hard to
hydrogen will
do,
not be used,
guys, to mute us and then
transport.
unmute us. Because it'll be hard for us to be able to signal you in a timely
If you're going
manner.
to use a chemical fuel, you should use CH4, not H2. But nonetheless, it is needed for industrial processes and can be produced just by splitting water, essentially.
I mean, something that's been done for decades and decades. This is not, rocket technology.
Yeah.
And lastly, a small part of the pie, but a necessary part of the pie, is sustainably fueling planes and boats. Shipping accounts for 3% of global CO2. It's ripe for electrification. Even with lithium iron phosphate, long-haul ships can be fully
So they're
battery
going
powered.
through all
So that's a great
modes
opportunity
of transport
to
at this point, not just
electrify.
land-based transport.
Energy density is a little bit harder for planes, but
talking
short
about
haul is
airplanes,
doable today
talking
with some
about boats.
improvements.
That's
We'll
the
get
first time that
long-haul
I think
underway,
I've
but
heard them refer
even in the
to
meantime, we can leverage sustainable aviation
non-terrestrial
fuels produced and stored using excess renewable
form, the
electricity. There's a lot of work going on in this
land-based forms of
space,
transport.
and it's not, yeah.
Yeah, I mean, to really get long-range aircraft and
Yeah, I'm way back
long-range
again.
shipping to use
It's probably a buffering issue on my
lithium-ion,
PC.
you need to redesign the ship.
So no delay on
not just,
YouTube, according to Mark. Well, that's good.
And the plane. To
The video
take
started
advantage of the
fuzzy,
fact
but
that
it's
it is a
perfect
new
now. Mundo Finance from
source of,
Brazil, welcome.
energy. It's a different architecture. So just like with an electric car, you wouldn't just...
One of the things we found in our
take a gasoline
podcast was
car and
pushing
stick a battery in it. That's
EV-type
very
boats
suboptimal.
through water. Takes an enormous
It's much,
amount of energy. Do you
more
remember that
efficient
ferry
to
up in
have
the
the
Bay
battery
Area?
with the structure of the
Yes,
car.
I do remember that.
30 kW per
And,
mile.
Wow.
you know,
Well, you think about it. We were
make it
talking
as-
in our last
make it
podcast
mass
about
efficient
a
and
boat
optimized
that
for battery.
has that
batteries.
insane
If
speed,
that's done
but
with
it's
aircraft,
10,000
you can get long-range
horsepower
aircraft,
and
Yeah.
uses 8 gallons in
that
3
are,
seconds.
with cells
Sure.
at around 450 watt-hours per kilogram, which you can buy it right now, actually. It's
Hey,
expensive.
Don King.
I think that price will come down.
So when we stack up all of these efforts, we end up with the numbers we shared at the beginning of the presentation. 30 terawatts, 240 terawatt hours, $10 trillion.
Our social media guys behind the other side of the curtain here are trying different things. So if you see us going away, let us know. Or if the audio improves, we can still hear it.
When we look at the electric vehicles, they have to grow 11x. Well, they grew 60% year on year last year. That growth rate is also going to close pretty darn. That gap is going to close pretty quickly as well. And lastly, storage. Tesla's energy storage.
Over here we
business
can
has
hear
grown
it clearly.
65% CAGR since 2016. The global, energy storage business is accelerating pace as well. I mean, all these gaps are going to close, especially as this momentum of the transition to sustainable energy accelerates. And of course, our goal on this page is 20 million EVs.
There's no solution to this.
20 million EVs per year. Is that what he just said?
That is what he just said.
Wow.
And then, what about this investment? How do I have a reference point on this investment? Elon mentioned it's 10% of, 1 year's world GDP. Another way of thinking about
Brad
it is how
C
does it
says he
compare to
can't
what we're
imagine wearing
investing,
sunglasses
like what
all
we
day
invested
inside and
last year
outside
in the
both.
fossil fuel infrastructure.
Brad, you're
and
gonna
it's 60% of that
have to try
investment.
it.
So actually,
It's easy to get
building
used
this
to.
sustainable energy economy
TikTok,
is
Meadow
less
King
than
183
extending
says, hold on, let
fossil
me
fuel
put on my
economy
sunglasses.
from a
That's the right
year-over-year investment
attitude.
basis. So very doable. When we look towards, does this fit on the
Now,
planet?
user
Absolutely.
has a
Less than
question. User with a
0.2%
bunch of
land.
numbers. Welcome back,
As a
by the way.
reference point,
Are you guys able
the
to
total,
downgrade Tesla
land
software to
area
earlier
intensively
software
farmed
updates?
Today is
Yes.
12.5% of all land.
We are.
So, I mean, you drive around, you see some farms, but you don't see them everywhere. This is an order of magnitude, more than an order of
Looks
magnitude.
like Brad
difference
C.
between
just put on
farming
his
and what we're
sunglasses.
talking
We have an
about
emoji
for
with
sustainable
sunglasses.
energy
That's
plan.
right.
That's the way to do
It
it.
doesn't need to displace farmland
Of course
or
not, yeah.
forests or jungle or any kind of ecological preserve. It can be used in very sparsely populated desert regions.
Yeah. Barren areas,
Yeah.
areas that are just not really fit for development or otherwise used. So,
Yeah.
I mean, 0.2% can fit into a lot of places.
Yeah, there's essentially no meaningful ecological impact. In fact, transition to a sustainable energy economy would result in a substantial reduction in current ecological impact.
That's a great way to put it.
Yeah.
And what about on the mineral extraction side? So this is a cartoon that sort of gives you a sense for all the ore and the extracted minerals that are coming out of the earth every year. It's about 68 gigatons. So each truck is a gigaton. What does this look like when we're in a sustainable energy economy? Looks like that. The fossil fuel extraction disappears. We replace it with the materials required to fulfill the sustainable energy economy. It actually reduces. Now, it's not to say that we don't need to continue to explore, bring on mining and refining for the sort of specific materials for the sustainable energy economy. We do. But the investment and mass flows are all very achievable, just looking at what is already happening on the planet. Like, this is nothing out of scale of what has been done and is already being done. And then when we calculate it on a sort of, element by element basis, the resources are there to support the transition.
So there are long
This is
moments of
cumulative
silence on our
demand
end here.
to move
It's
in the
because it's a
sustainable
very
energy economy
technical
direction until
presentation,
2050 relative to
and we are
USGS
absorbing it.
resources today.
I'm sure we'll
We're
go
not
over
breaking
it
the resource
after
bank
this
for any of
session
these
and
materials. And
go
then when
over
we
it in
look
greater
at
detail.
what really happens as we move
But
forward,
I think that these types
history
of
teaches the more we look, the
presentations
more we
eventually
find.
move into
What people
something
think
a bit
happens is,
more or less
oh,
technical,
there's
let's
this many
put it that way.
resources, next year
I
there's
think
gonna be
so
less
as
if we're gonna
well.
extract them.
As we
What
get
actually
into the
happens
third
is,
part of their
as we,
presentation and how they fit
extract
into this
resources,
grand
we
vision
find
that
more.
they're going to
And you
have,
can see on the
we're
right
going to be
what has
able
actually
to
occurred with the
see a
key
lot more
materials to the
practical
sustainable energy economy.
stuff come
Since
from them and
2000,
be able to
as the
comment
sustainable
on it.
energy economy
I'm
has
going
been
to
growing
take
and
notes
Tesla's been
down
growing
on
and
things that
all
I
the
find
industries around
notable
us
as
have been
well,
growing.
like the
The
less
actual
mineral
resource
extraction
availability has
that they're
increased,
talking
not
about.
decreased.
That'll be good for
Yeah,
us to
so-
comment on later as well.
There still seems to be quite a bit of confusion about lithium. Lithium is extremely common. It's one of the most common elements on Earth. There's no country that has a monopoly on lithium, or even.
So Oliver Topaz
close to it.
asks, do you think we'll get
there's
introduced to
enough
the Tesla
lithium,
coil?
Or in the United States?
Probably
to electrify all
not.
of Earth. If the United States was the only place
But that
producing
is a cool
lithium,
device.
there's enough domestic material to electrify Earth.
We built one of those in high
It's
school, by the way,
Very common.
before the age of
The
PVC.
limiting factor.
And we
is
used a
the
carpet
refining of the lithium
tube,
into battery-grade
carpet roll
lithium
tube.
hydroxide or lithium carbonate.
And
That's
the
actual
students
limiting
took
factor.
turns
And the same
after
is true for
school
these other materials.
Yes.
winding
This is, again, these are
wire
not like crazy
onto this
technologies,
coil.
it's just the investments need
We
to
had
be
it
made,
mounted
and
on
the
a
investments,
lathe, a long
they're not
lathe,
gigantic, they just
and
need
we
to
had
happen.
30 gauge wire, very
Nickel's
thin.
maybe the
And you
of
have to
them all,
sit
the
there and
trickiest
just
one
kind of
to-
let this
to
thing
solve.
turn
But as
slowly and
we showed
add
with the graph there, maybe need like 30%
windings
of the ones
onto
that
this
got
coil
nickel
until
reserves.
it
So,
ended up
And the
being a
nickel
4-foot
reserves have
coil.
actually grown, so
Oh
Yes.
goodness, that's a lot of wire.
There is more. Yeah, exactly. So.
We then
you
used
only need
a
nickel
neon
for,
sign transformer,
basically
15,000 volt
aircraft, long-range
transformer,
boats,
and
very long-range
piped that into the
cars.
primary windings, which is
But
only about
the-
20 or
the vast
30
majority of
windings
the
using
heavy lifting,
spark plug
for electrification
wire,
will be,
which is able to
iron-based,
handle high voltage.
cells.
and
And
made our own
Earth is-
capacitor with
iron is
two
actually literally the
some
most
pieces
common
of
element on
glass and
Earth.
tinfoil,
So,
high voltage capacitor.
trivia point.
And the
say,
thing
like,
would
what is
throw a
Earth made
4-foot
of?
arc.
By
Problem
mass,
was
it
that
is most- it is
all
made
the
of
television
iron more
sets
than
in the
anything else,
neighborhood
and
would
second,
die, get
oxygen,
fuzzy when this
and
thing
then,
was turned on. And eventually the neighbors
everything
figured
else
out there was
after that.
something
So
happening at that high
basically
school
we're
that
a-
was affecting their
muddy rust
reception.
ball is
So
what
it became
Earth is.
restricted.
So an iron cathode is sort of, you're definitely not going to run out of iron. There's so much iron, it's insane.
User has asked how much the software downgrade would
that's-
potentially cost.
You know, there is some
Yeah, and
consulting
ultimately,
time
this
involved,
resource,
and there may
extraction,
even be
we go
the
through
necessity
this
for
effort, we
sending the
built these
Tegra board to
batteries,
us.
and
So I would
then
have
we
to check
recycle
with
these
our
things.
service
So
guys.
ultimately,
If you want to
we're
email
doing
that
this to
request
build
to
this
us at
sustainable energy economy, but the
ev@gruber.com,
maintenance amount
they
of-
can get you a much
of
better
ore that we
ballpark
require
figure.
is really an order of magnitude or more, less because of recycling. So in the end, a sustainable energy economy is within our reach, and we should accelerate it.
Yeah, I mean, so this is really the main message of today. And I really wanted today to be not just about Tesla investors who own stock, but really anyone who is an investor in Earth. And what we're trying to convey is a message of hope and optimism. And optimism that is based on actual physics and real calculations, it's not wishful thinking. Earth can and will move to a sustainable energy economy, and will do so in your lifetime. Thank you.
Yes. Thank you. And I just want to welcome up Lars and Franz to the stage.
Who's coming up?
Lars and Franz.
Oh, Franz von Holzhausen. I don't know who Lars is.
Hi. Hi, I'm Franz. I lead design at Tesla.
And I'm Lars. I've been doing vehicles with Franz for almost 13 years now.
13 years, okay.
So I joined Tesla in 2008 to vertically integrate design into the company. It didn't exist before. It was a pretty small team. It was tasked with designing the most beautiful, innovative, and well-engineered vehicles on the planet. No small task in 2008. There was not a lot going on in the EV sector then. Since then, we focused on constant improvement in cost, efficiency, innovation, things that you'll continue to hear about today, while continuing to design the most desirable cars. Today, we produce cars differently than we did 10 years ago. But the end result is always an exciting, futuristic, and desirable set of vehicles.
Back then, we only had a handful of designers and engineers like myself, but we had a great vision to radically change transportation.
So back in 2008, where we were designing Model S, we didn't have a factory. In fact, we had a really small engineering team and a tiny design team. But that allowed design to lead all the conversations. It let us innovate forward-thinking ideas, like how do you fit 7 people into a sedan? Or how do you make door handles disappear?
Yeah, Smart, your comment is true that these guys were true
or
early
putting
disruptors.
a huge touchscreen into the center of the vehicle, something that had never been done before.
And then we won Motor Trend Car of the Year.
Yes, and we won Motor Trend Car of the Year in 2013. Our first, great award, first car. Pretty good start. Kind of a home run, I think. But that whole process resulted in a linear process that you see on the screen. We designed first, then we engineered, and then we figured out how to manufacture it.
Yeah, I mean, I think that's really important. When we were designing the car together, we didn't even know where we were going to build it. And so we came up with
I didn't even know Lars when we were designing.
That's true. So once we got Fremont, we were very fortunate, and we figured out the manufacturing solutions sort of like we were flying a plane and putting the wings and building the engine at the same time. So we knew we had to do better.
Yeah, we knew we had to be better in order to scale. And as part of the master plan that you've read, Model 3 needed to be a smaller, more efficient, and more affordable version of Model S. But it had to be equally great. It had to have all the things that people loved in their Model S or Model X, but be much more affordable. And so we approached the process a little bit differently than the first time around. Now we had teams that we all worked together, so we were able to combine design, engineering, and manufacturing process all at the same time. But somewhere along the way, we changed the manufacturing process to be fully automated. And so we leaned into this whole new way of manufacturing a car, but we had already engineered it. So things didn't quite go as well as planned.
It was an amazing product, but it landed us in production hell. Many of us who lived through that
Elon having to
carry those battle scars.
work
It was a great
120-hour
idea, but
weeks
it
to
wasn't
help
the
make
right
sure
timing.
the production got going for
Like
the
Franz
Model
said,
3.
automating something that we designed
the
to
term
be built
production hell.
manually is
Yep.
super hard. And we have many, many failed examples of that at the Fremont factory that we ripped out. But some of them eventually still work. This is one I actually worked on with a small team of engineers. It's still running today. And some of the engineers that came by said we couldn't do it are no longer with the company, but it's running, and it's running faster than ever. So we kind of self-imposed constraints on the design when we were doing it to be built manually, and we really didn't think about it. But despite all that, Model 3 is the best-selling EV ever.
Yeah, and Model Y, which is derived from Model 3, is about to pass that. But we knew we had to improve the process further. And with Cybertruck, we designed a vehicle around a vision that actually started with the manufacturing process. And in this case, the materials dictated the design.
Forming full hard stainless steel isn't rocket science, but it sure isn't easy, and it limited the way we could do it.
Yeah, absolutely. It really forced us to think about designing something in a way that you couldn't normally stamp panels, you couldn't form them in a traditional way. So you ended up with very linear bending processes that are just not in automotive kind of language of manufacturing today. But it actually created a very efficient process and one of the most dynamic designs ever, I believe. It's definitely something that's going to change the road landscape.
Hopefully you guys saw it down there and you experienced it. It's definitely real. Those are real trucks. We're on our way to build them. But what that stainless steel opportunity did for us, it has let us rethink the factory footprint. We don't stamp those. That's a huge part of it. We don't even paint them. So our footprint got smaller, and we started to think about innovative ways to take those
That would be
constraints
interesting, wouldn't it?
and make great products.
They've been moving some
But that
around the
constraint didn't really
country
change
most
the end
recently.
result of the truck.
So yeah, there's a good
It's a
probability
super
they'll
dynamic truck, and it
come
has
up with
all the
something here.
functionality you would expect out of any of the other competitive trucks. And the best thing about it, it's coming this year.
All right, we've got
So ideally,
a shift here.
after all that, we would design, engineer, manufacture, and plan for automation happening together. It gives us the opportunity to question requirements. This is something that is fundamentally only available at Tesla. In the places I used to work and the top manufacturing companies in the world, they don't sit together.
Yeah,
We are one team.
Nowhere I know has all these teams together thinking about these processes from the very beginning.
In fact, all of those engineering teams, manufacturing, design, automation, they're all in one org. They all report to one person.
you
We
a
can't
movie
point
buff
fingers
at
at
all?
each other. So we have to solve
On the
them
what?
together,
A movie
which is
buff?
the best way to innovate.
No, not really. I don't know what
Traditional
he's
way of
talking
making a
about.
vehicle is
Chris,
that you stamp it, you build the body in
Bransfield
white, you paint it, and you
is
do
asking
final
about
assembly.
Weekend at
And what's
Bernie's.
interesting is these
It's a movie
shops
about a
are
guy
dictated by
who dies,
the organizational structures
but,
that exist, and they're
a
dictated
group of
by the boundaries
teenagers,
that exist in
college
the
age,
factories that are laid
was
out.
going to be
If something goes wrong in final
ends up
assembly, you block the whole
keeping
line,
Bernie,
and you end up with buffering in between.
sitting on lawn chairs,
This is at
working
the
with him,
tail
and Bernie
end
always has sunglasses on, so you
of
can't
its
tell if he's alive or dead.
manufacturing optimization.
Okay.
Henry Ford first invented this assembly line in 1922.
And how long
It's
did
been
this go
100
on?
years, and it's
Oh
really hard
goodness,
to
there
make
are
a
a couple
change
of
after
movies
100
about
years.
this. The first Weekend
And
at
when you
Bernie's
watch
was
it
several
happen,
years
it's
ago, but it was very
actually really
humorous. It was a
silly
good
to
movie.
a guy like
I
me.
could imagine.
You take all these stamp panels, you put them together,
But we are moving,
then you
so
put them in a
we are,
filing
yeah,
station.
yeah.
Yeah,
You
we're
build
not
a body
Bernie.
that looks
We're
something
alive.
like a car.
And we're
You
animated,
put the
yeah.
doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings
I
that
think he
already
makes a good
exist. I
point.
wish it went in like
When
this
you
big piece
fragment
like this,
your
but there's
design
actually
team,
people
or any
coming in
teams
and
for
out
that
of the
matter,
car. There's awkward,
cohesiveness
movements.
tends
Then we
to
lift
get
the
lost
car
a
up. We
bit.
put stuff from
Yep.
underneath it. We put it down. Then we put the seats in the car, and finally we
I think
close it
they're
all out
about
with
to
glass, and
announce
we
a
bring
whole
those
new
doors that went away
manufacturing
for a
process
trip.
that's going to make the
and
car
put them back in the car.
building go faster.
Interesting.
Most of the
Let's
time,
see.
we're doing this with a big, giant car and moving it and doing really nothing to it at all.
What's funny though in this kind of whole process is that just recently Toyota just called this an engineering work of art.
True.
Great animation.
The Model Y.
That was humbling, but at Tesla, it's not good enough. If we're going to scale the way we want to do, we have to rethink manufacturing again. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings, and we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats in the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought maybe we could do this other places.
Yeah, I mean, in a way, the constraints become part of the solution rather than a problem.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. I call that space-time efficiency. It has nothing to do with quantum mechanics. We can have that conversation later. But we get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently, we only paint what we need to, and then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it, and it means we're doing more work on the car more of the time. And then, when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption
Smuggler,
of
I hope you
electric
have a good
vehicles on
drive
the
home.
orders of magnitude that we just showed you,
Thanks for
we have
joining
to
us.
make
It
constraints
says it's
part of
after
the
5
solution.
and I have a
It
45-minute
leads us
drive
to
home.
greater than
Take care.
40% reduction in footprint, which means we can build factories faster with less CapEx and more output per unit. Faster, less CapEx.
I'm wondering if
more
Smuggler's
output per
correct,
unit
too, if they're
dollar.
going to mention any new
Zach's going to
battery
go into more
material.
details on this later, but it also
haven't
means
talked about
through
salt
this
yet.
innovation
No.
and some
The
of
sodium
what my
battery.
other engineering colleagues are going to talk to you about in the future, we'll reduce costs as much as 50%. This is the 2-for-1 concept you hear me and Elon talking about on earnings calls.
Yeah, so I think our track record proves that we can deliver the best cars, and we deliver the best cars in spite of, because of these constraints. And I'd love to really show you what I mean and unveil the next-gen car. But you're going to have to trust me on that until a later date. And I promise we'll always be delivering exciting, compelling, and desirable vehicles, like as we always have.
Have we ever not? We
Yeah.
always do.
But what else is Tesla known for?
Speed. So with that, I want to bring on Colin, who's in charge of making our cars go fast.
So that's a little bit notable
Thank you,
to me.
Lars.
He
Thank you,
specifically
Franz.
did
My
not
name is Colin
announce
Campbell,
anything
and I
from
have the real
cars yet.
privilege
We'll
of
see
leading
whether or not that's
powertrain
going to come later
engineering
today.
here at Tesla. We make the fastest cars that you can buy for the money, whether they're electric or gas. And the Model S Plaid that we're looking at here, it has more than 1,000 horsepower, and pound per pound, the motors in that car are as powerful as jet engines. Our cars are super fun. People absolutely love driving in them. And the other thing that you probably all know about our powertrains is that they're efficient. Our cars go 25 to 30% further than other EVs in our class for the same amount of efficiency. But at Tesla, efficiency means more than just reducing how much energy the cars use. It's about how we develop, how we manufacture, how we refine, and how we scale the powertrain. Now, the Model 3 and Y powertrain is a great example of this broader meaning of efficiency. So since we launched it back in 2017, we've continuously improved that powertrain and the factory that builds it. So the drive unit, the engine of the car, is 20% lighter for the same power. We use 25% less heavy rare earths than when we started. And the powertrain factory, which is behind me today, is 75% smaller and 65% cheaper than the one that we originally built. And what I really want to emphasize is that we did all of this without compromise. Our cars are just as powerful, they go just as far, they cost the same or less, and the factories have the same output. So, how did we do that? We did it by designing the entire vehicle and the entire factory together as one company. And this sets Tesla apart. We have small and highly capable teams, and to make a critical decision, we can have the battery cell chemists, the mechanical engineers, the manufacturing engineers, the supply chain team, the automation designers, the software programmers, all in one room, working together in real time. And that allows us to make decisions that are best for the whole car and to make them really fast. And that approach is unlike traditional automotive engineering, which is really fractured. And if you were to go buy like a premium German electric car, the engineers who designed the drive inverter in that car, they did not work for that car company. They worked for a contractor. And at Tesla, we designed the entire car and the factory that builds it. And I want to highlight a few examples of what we've been able to do in-house thanks to that unique approach. So, inside the charger of your Tesla are transistor packages, and that's at the top of your screen here. And every electron that moves you down the road flows through one of these packages. We designed our own custom package, which is what you're seeing here, and we can extract twice as much heat out of that package as what we could buy off the shelf. And so what does that mean? It means that the silicon carbide wafer that's inside those packages can be much smaller. And silicon carbide is an amazing semiconductor, but it's also expensive and it's really hard to scale. So using less of it is a big win for us. And then on top of that, orchestrating all of these transistors and making them switch in the right ways is computationally extremely intensive. It used to require 4 microprocessors, which are shown here in the bottom left. We have developed our own custom microprocessor. It's purpose-built for high-power electronics. It's half the cost, and it does, in just one, the job of all of those 4. And these are just 2 examples of many that I could use to showcase our expertise in high-power electronics. And that expertise has allowed us to take the cost of the chargers that were in our Model S when we launched it in 2012, both the cost and the mass, and cut both of those in half.
Joey V, do you have a partner company on the East Coast that you recommend to fix my Model Y?
They're also central to our superchargers.
I would say on the East Coast, Rich Rebuilds would be a good choice for you, up in Seabrook, New Hampshire, and
So in addition to the work that we've done in software and hardware, we've also done a lot of work in-house on software. So this is the drive unit for Model 3 and Y, and if we take a cross-section, we see the stator and the rotor, and they're responsible for the core function of the drive unit.
Thank you for telling us where
which is
you're at,
converting
Bethany.
electricity into motion.
Bethany is next door.
And our custom software lets us simulate the rotating magnetic field that is responsible for that conversion. And getting that
One of our employees
simulation
or a neighbor?
exactly right,
I can't tell.
it's central to the cost,
Bethany doesn't ring a
the
bell.
weight,
I think
the
she's going to
size,
be our neighbor,
and
possibly.
even the sound of the drive
Yeah?
unit. And now, you can buy software that will do all of this, but our tools are faster, and they're more accurate, and that was not easy to do. And that allows us to quickly iterate through millions of possible drive unit designs to find the best one. I want to highlight one more area where Tesla really excels because we integrate work that is often farmed out. So when you are making a new product, it's not enough to think about the product itself. You have to think about how you're going to make it at scale. So at Tesla, our powertrain and our powertrain manufacturing equipment is both
That
designed
is
under
over at
one
Hot
roof.
Rods by Dean.
The engineers who are designing
okay.
the motor,
That is next
they are in
door.
the same
Well,
room
welcome.
as the engineers who are designing the machine that's going to put that motor together. And that collaboration pushes us from day one to design products that are not only high performance, but are really easy to assemble. So, all of this expertise that we
Lee
have in
is
the
asking,
powertrain
is it
team,
cold
in
in
hardware,
California?
software, in
Jet,
manufacturing, it's going to have a major impact
will
on our
admit
next
it might
one.
be, but we're in Arizona, so we don't know if it's cold in
In our
California
next
at this point in
powertrain.
time.
So those silicon carbide transistors
Cold
that I
to
mentioned
us
that are
means
key component, but
55
expensive.
to
We
65.
figured out a way to use 75% less without compromising the performance or the efficiency of the car.
Ooh, the pillow
Of
is
course,
up
we know
on the
that battery
screen.
cell supply
Yes.
is one of the constraints on the scalability of EVs right now. Our new powertrain is compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000. And we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. All of these improvements, I think, are going to be transformative for the adoption of EVs and our ability to scale them. There's one more thing that I want to highlight. So I talked about how we had reduced the amount of rare earth in our powertrains. And as the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this.
Is that after
We have
the work you
designed our
did?
next drive unit,
It's at
which uses a
1:47
permanent magnet
p.m.
motor to not use any rare earth materials at all. So how does all this fit into the master plan?
We'll have to take a look at that
We
once
can make
we're,
lower cost
once we're
products
off
that are
air.
still efficient and compelling, and we can make them at scale. We're going to use less of constrained commodities, silicon carbide, rare earths. We're going to build them all in compact and high output factories that are easy for us to build quickly. We're going to make that easy to scale powertrains all the way up to the levels that Drew and Elon mentioned at the beginning. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do. Thank you.
We're talking about potential smaller factories to do the same output.
So next, I'd like to welcome my colleagues Pete Bannon and David Lau.
Which is inconsistent with their Gigafactory growth plans.
Good afternoon, everybody, and welcome to Texas. Pictured here is the low voltage system of a Model S from 2012. This car was primarily designed with vendor source controllers integrated by Tesla. There are over 300 low voltage devices that encompass everything from the mundane, like the light in the glove box, to the complicated, like the infotainment computer, to the safety critical, like the airbags, steer-by-wire, and brake-by-wire. The low voltage harness is built from individual wires, cut to length, crimped, and inserted into connectors, a manual process that is tedious, error-prone, and doesn't scale well. Going forward, we want to reduce the size and complexity of the harness and enable automated manufacturing.
These wire harnesses introduce extraordinary complications, especially in the early stages of development and bring up of a vehicle, because when we're trying to bring up this entire system and we see that it's not working properly, we don't know whether it's a problem with the software, with the controller, the processor, any of the endpoints in this entanglement of wires. And so we have to go and debug everything all at once. And Pete's going to tell us about how we're going to make it better.
So I'm going to talk briefly about a few things that we've changed over the years since the Model S. With the Model 3, Tesla started designing an increasing share of our controllers by merging controllers together, and we were able to simplify the design with a significant reduction in wire count and weight. Going from S to 3, we reduced the wire harness by 17 kilograms compared to Model S. And this is a pretty big deal. And just to put that into context, our VP of Engineering, Lars, We'll deliver a bottle of your favorite spirit to your desk if you manage to save a kilogram of weight from the car. So this improvement cost him quite a lot. Did we skip one? Yeah. The original Model 3 controllers were enhanced and then built into Model Y. Those improved controllers were then moved back into Model 3 when we introduced the heat pump. At that point, we had shared controllers across both cars, which helped simplify our supply chain. Those Model 3 and Y controller designs were then updated and enhanced for the new versions of Model S and X that we introduced in 2021. For Cybertruck, we are now designing 85% of the controllers in the car. For the next gen platform, we're going to finish the job and be designing 100% of the controllers to give us full control of the design and the supply chain at the component level. Having full control of the supply chain at the component level has been critical to Tesla over the last few years as the supply constraints have hampered our ability to build cars.
And with that control comes control over all the software, which enables us to develop features and functionality that we never even dreamed of at the time we designed the hardware. So that's why you see software in your cars getting better and better over time in ways that we didn't even think of when we designed the hardware in the first place.
Mm-hmm. Yeah, Sentry Mode is one of my favorite last-minute changes.
One of my favorites.
With the introduction of Model 3 in 2017, we deleted relays and fuses from the car in favor of e-fuses. E-fuses replace moving parts with solid-state transistors. They provide fine-grained control of the power system to software and allow software to do advanced things like load shedding in the car under adverse conditions. E-fuses also allow for software-controlled retries for transient faults, and they allow for detailed monitoring of the power system over time.
Yeah, the theme you hear a lot about today is software-controlled hardware. And when I think about that in my team, software-controlled hardware is fundamentally about being able to sidestep what otherwise would have been static trade-offs between one attribute or another in a piece of hardware. We are able, with software, to instill intelligence, context awareness, and context-specific behavior into what otherwise would have been a piece of hardware that had to get optimized for one type of scenario. We get more of everything.
In 2022, we completed the transition from lead-acid batteries to lithium-ion batteries, and which use a new toolless connector. We expect lithium-ion batteries to last for the life of the car, so don't expect anyone to wake up to a dead battery ever again. This eliminates a major source of failures for our car. And the toolless connector makes it easier to service the car, and it also includes a software feature to allow validation that the connector has been properly installed at the end of a service event, which removes another source of failures in our cars. Obviously, the mass and volume savings are also significant, which is super helpful. At Tesla, we're always trying to improve every single component in the car, and a nice example of that is the 15-inch display that was originally shipped in the 2017 Model 3. Over time, the cost of the display has gone down 24%. We've been able to reduce the weight by 12%, and we've reduced the power by 33%. At the same time, we've increased the brightness of the display by 50% and improved the color accuracy. So this is one of our favorite things at Tesla, is to make a component cheaper and better. At Tesla, the drive to improve efficiency in the car is never ending. I think of it as like peeling a carrot. You just take a swipe at it, a little bit falls off, doesn't really make much of a difference. But if you just keep at it, over time it accumulates into a pretty significant improvement. One of the changes that we're looking to make right now is to change something that's been steady for the last 60 years, 12 volts. 12 volts has been, as I said, for 60 years. The demand for power in the car has been steadily increasing to the point where we now have to have pretty large wires to drive over 200 amps of current around the car, which increases the mass and cost. With Cybertruck and all future Tesla platforms, we will be moving to 48 volts. This reduces the current needed by a factor of 4. And since power loss in the harness is resistance times the square of the current, a 4x reduction in current leads to a 16x reduction in lost power while distributing energy in the car. That allows for smaller wires, smaller e-fuses, and smaller controllers. It also allows us to make those heat sinks smaller, or in many cases, remove it completely, all benefiting the car in terms of mass and weight. 48 volts is the future for low voltage design at Tesla, and likely the rest of the industry in due course.
We welcome and encourage other OEMs and the entire supplier network to join us on this evolution.
So for those of you watching, we're going to go full screen on the
number of wires in the car is driven
broadcast,
by the number of endpoints
and
that need
we'll
to
be in
powered
background
and
mute,
controlled.
collecting
In the
notes.
past, centralized
So
control
continue
has
to
left
ask
the
your
wires
questions,
spanning
we'll
the
collect
entire
them,
car.
and then
For
we'll split the
Cybertruck
screens
design, we
again
have moved to a local
once the
controller
presentation is done.
where the wire is connected to the nearest controller.
With the exception of
and those
Instagram,
controllers are
okay.
Connected over Ethernet. Wires are routed to the
Okay.
nearest controller where the data is converted into a network packet for transmission to the correct location in the car. To be effective, the network must be reliable, have low latency, and low jitter, and these are all attributes that we've been able to achieve with the current design. The design has delimited most of the cross-car wires in Cybertruck, and with the next-gen platform, we're going to finish the job and eliminate all of them.
This consolidated vehicle network allows us also to make a whole lot more dynamic changes on the fly to how components in the vehicle talk to each other, rather than the traditional approach of separate CAN buses that are spread throughout the vehicle and fixed in hardware.
And one of the nice things is that you can see the entire vehicle through a single connection, which wasn't possible in the past for debug. For the next-gen platform, we're looking to optimize the controller design across the entire car and across all of the organizations, not just for a given subsystem. Simplifying the wire harness will enable automation. 48 volts will allow us to reduce the size, mass, and cost of the low-voltage system, and it's one of the key things to enabling us to scale production of the low-voltage systems for the Master Plan 3. David?
Cool. So I joined Tesla in 2012, and even in those very early days of the Model S, we already had the ability to update software over the air in all of the controllers throughout the entire vehicle, at a time when other cars were just starting to update software in only their infotainment units. And furthermore, we've had sophisticated, anonymized data logging and telemetry capabilities that allow us to understand how the fleet is doing, what customers are doing with it, and how it's responding in the field to that usage. These two capabilities combined, OTA updates and data insights, give us the ability to iterate quickly on our software and to maximize the amount that we learn and proceed and the progress that we make in every one of those iterations. We've used these capabilities to inform countless design decisions in both software and hardware.
Yeah, one example is that we were able to monitor and track the use of the sunroof in our cars and found that our customers never use their sunroof, so we made this easy decision to remove it.
Very barely, yeah. We haven't had sunroofs for a while. As another example, we are able to use our collision data to design our crash safety systems for what happens in the real world, far beyond what regulatory and consumer ratings tests prescribe. And then furthermore, we're able to use that data to recreate in simulation all of those crashes every single time we make a change to the vehicle's design or to the software that controls the airbags and other restraint systems. Here on this graph, the gray dots that show up first are specific crash tests that are prescribed by regulatory and consumer ratings agencies throughout the whole world. And the rest of the color that fills in around and on top of it, those represent the crashes that we've seen happen in the real world. Those are what we design for and what we test to.
Right, and last year this data was used to change the algorithm for seatbelt tensioning to reduce injuries in the field, which was OTA to all of our cars.
Here are a few statistics that demonstrate how staggeringly quickly we gain new insights from the anonymized data that we've received from the fleet every day. Every day, 123 million miles driven, 1.9 million charge sessions, and those rates are only increasing as we deliver more and more cars into the world. As another example, we've analyzed patterns in the way the fleet drives and charges to optimally size battery packs for our next generations of vehicles. And you'll hear lots of other examples throughout the rest of the day about how we're using data to inform decisions in the product and in manufacturing. So you've heard a lot from Pete, Colin, and others about how important vertical integration is for us in hardware, but it's especially important for us in software. And this is extremely difficult from the way the rest of the traditional automotive supply chain is set up. In most situations, all the controllers in the car are delivered by different Tier 1 suppliers, whose software is written by Tier 2 suppliers, who farm some of that software out to different Tier 3 suppliers, and so on and so on. Making a change that spans multiple components takes months of coordination before any work can even start. And furthermore, integration of software in the server side with what's happening in our vehicles has always been a core part of our DNA and enables us to do things that nobody else can. Most engineers think about the vehicle as a complete, consolidated, fully contained system. But in the software team, we think about the system as including the vehicle as well as all of our back-end server-side applications and infrastructure and the resultant feedback loop from the entire fleet that informs all the decisions we make as an engineering team. For example, we recently released a feature in Model S and X that automatically, predictively adjusts and raises the suspension for ride comfort before the car hits a section of rough road. We do that by leveraging the fleet to generate a map of road roughness everywhere our cars drive. Sounds pretty simple, but requires coordination of software across a number of different components inside and outside of the car. The restraint control module, whose inertial measurement unit senses the road roughness, the autopilot computer, whose GPS module and localizer figure out where the car is in the world, our navigation server, which aggregates the anonymized telemetry from the fleet and annotates our map with things like updated speed limits, lane topology, and now, road roughness. The onboard navigation engine, which looks ahead of the route that the car is traveling on and determines whether things are about to get rough. And finally, the air suspension controller, which takes all of those factors into account and decides continuously whether it is appropriate to adjust the suspension for ride comfort. And before we released this feature to the world, we sent prototype versions of it to the entire fleet that ran passively in the background, sending us anonymous data about every time it would have engaged, which taught us exactly how it was going to behave in the wild, in every environment, in every circumstance.
Yeah, being able to test new algorithms in the background without impacting the car is really critical ability for us, especially for safety critical things like automatic emergency braking.
And we've used it to iterate on early versions of our stability control algorithms, which were introduced to the entire Model 3 fleet in 2017 with extremely high confidence, even on a very foundational and safety critical function. Okay, so far you've heard me talk a lot about how we leverage our software systems to iterate quickly on the customer-facing product. But what I haven't talked about, and what we haven't said much about publicly in general, is how we leverage these capabilities in our own internal operations. So for example, in the early days of manufacturing Model S, we very quickly realized that there are a lot of different ways you could misassemble a car. You could forget to plug in a wire, you could not fully set a connector, you could pull a part from the wrong bin. So when we designed our manufacturing processes for Model 3 and all of our other vehicles going forward, we took a page from the software playbook, which says, test early and test often. And we applied that mantra to every single car that we build at every step of the assembly line. So now, when a production associate plugs something into the car, the central car computer sees that connection, confirms that it's the correct part for the type of car that's supposed to be built, installs a software update if necessary, checks configurations and calibrations, and runs a barrage of tests on that thing and all the other things that are connected to it. And if it finds an anomaly that can't be fixed purely with software, it throws an alert immediately that is displayed prominently on the vehicle's display, as well as sent to back-end command and control systems, so that a human can come over and fix the problem before the rest of the car gets built on top of it. And we're taking a similar approach in service through a combination of onboard vehicle diagnostics, natural language processing applied to customer narratives when a customer schedules a service appointment, and a suite of internally developed tools. We are successfully diagnosing, scheduling, and ordering parts for over 33% of customer concerns in service.
Yep, and we also use testers built around our own controllers to test sub-assemblies before they get to the car, which will be even more important as we go to Lars's unboxed assembly strategy.
100%. We'll know with extremely high confidence that before those boxes get put together, that they themselves are assembled correctly. Okay, you've heard at lots of other events about all the awesome things that our autopilot and AI teams are doing to make the car drive itself, bringing us into the future of autonomy. But we've also been thinking for years about all of the other pieces that we are going to need to manage a network of autonomous vehicles. A lot of this has been happening behind the scenes in the form of platform-level functionality that we'll leverage later. But you've seen some of it surface already in terms of features that our customers and our internal operations teams can benefit from. Like in 2021, we built on top of our mobile app phone key and gave our customers the ability to share their car with anyone by sending them an invitation in a text message or an email. Last year, we introduced profile synchronization, which synchronizes your seat, steering, and mirror positions, as well as your settings, media favorites, and stored navigation locations across all vehicles in your account. Internally, we have an app that allows our personnel in engineering, manufacturing, delivery, and logistics to view, locate, and drive all Tesla-owned vehicles at their site. And when customers bring their car into service, when they receive a Tesla-owned service loaner vehicle, we are starting at some locations to automatically add that vehicle to the customer's mobile app account, so that combined with cloud-synchronized profiles and phone key, it's a completely seamless experience. As soon as the customer walks up to that loaner, it behaves and feels exactly like their own car. And all this is built on top of end-to-end encryption and cryptographically signed commands, so that customer data remains private and obscure, and the fleet only trusts commands from authorized parties. So that's a bit of a preview of all the pieces that we're building, looking ahead to our future of autonomous fleets. Synchronization, permissions management, security, and privacy. And that has been a whirlwind tour through some of the things that we're doing behind the scenes to enable the efficiency, cost reduction, and speed that we are going to need for our next phase of growth and for the next phase of the master plan. And so now, to tell us about the latest in full self-driving, I'd like to introduce Ashok.
Thanks, David and Pete. Hey, everyone. My name is Ashok Elluswamy. I work on autopilot and self-driving at Tesla. I joined Tesla back in 2014, so I've been working on this problem for almost 9 years now. Yeah, some of you might be wondering, hey, what does self-driving got to do with the plan to a sustainable future? But it's actually a critical part of this plan, and here's why. Currently, when the car is not being used, it is sitting idly in parking lots, not doing anything. But when autonomy is truly unlocked, this car, instead of being idle, can go serve other customers. This fundamentally reduces the need to scale manufacturing to extreme levels, because each car is being used way more. But this is no trivial problem. Building a scalable self-driving system is, I think, one of the hardest real-world AI problems out there right now. Nonetheless, we at Tesla have made significant strides in making one of the most general systems at solving this problem. There are 3 main parts to get right to build a scalable problem. First is the architecture of the AI system. Second is the data. And third is the compute. We'll start with the architecture. At Tesla, we are betting on AI, machine learning neural networks to help us build a general vision and planning system. In the early days, we used to have single camera, single frame neural networks that produce some outputs. These were stitched together in some post-processing steps for the planner. But this was very brittle and was not leading to great success. So what we did in the last few years is transition most of our stack into this multi-camera video neural networks. These neural networks take in the live feed from the car in real time of the 8 cameras in the car and produce a single unified 3D output space. There are many tasks that we produce, such as the presence of obstacles, their motion, lanes, roads, traffic lights, what have you. This is one example output that you're seeing here. This is from our occupancy network that predicts the positions of obstacles and their motion. You can see that it precisely captures the swervy, violent motion of this truck next to us. And this helps the planning system to avoid a collision with this object. Some of the tasks, such as lane connectivity, are more complicated to model using naive methods in computer vision. So we don't stop at the computer vision techniques, but we reach out to techniques in other areas, such as language modeling, reinforcement learning, to model this task. This is similar. These networks use similar techniques, such as transformers, attention modules, autoregressive modeling of tokens, similar to what large language models like ChatGPT do out there. With such an end-to-end system of solving perception, we have really removed the brittle post-processing steps and produce high-quality outputs for the planning system. Even the planning system is not stuck in the old ways. It is now starting to use more and more AI systems to solve this problem. The neural network-based planners are needed especially in complicated urban planning when there's a lot of other objects interacting with us. This is, for example, an intersection where we have to turn left while yielding to crossing objects and to the pedestrians crossing the road. We have to do this both safely and smoothly while respecting everyone's right of way and preferences. If this was done naively, each configuration would take 10 milliseconds of compute, and there are easily thousands of configurations to reason about. This would not be feasible using traditional compute. But using AI, we have packaged all of this into a 50 millisecond compute budget so it can run in real time. The second big piece of this puzzle is the data. This is where Tesla has a unique advantage because it can tap into the fleet to access the exact data that can fix the problems. But raw data is not sufficient. In order to train these networks, you need labeled data. You need labels to supervise the networks. And if you only depended on the human labelers, this data would be too tiny to train these large multi-camera video modules. We need lots and lots of data to train these networks. Hence, we have built a sophisticated auto-labeling pipeline that collects data from the fleet, runs computational algorithms in our data center, and then produces the labels to train these networks. Here, you are seeing a 3D reconstruction that is happening by collecting various clips from different cars in the fleet and assembling all of them together into a single unified representation of the world around the car. You can see all the lanes, the road boundaries, curb, crosswalks, even the text on the road being accurately reconstructed by these algorithms. We don't have to stop at this kind of reconstruction. Once we have this base reconstruction, we can build various simulations on top of it to produce an infinite variety of data to train for all the corner cases. We have a capable simulator that can synthesize adversarial weather, lighting conditions, and even the motion of other objects to test all the corner cases that might even be rare in the real world. Here's an example of why this data is critical and how we can solve problems using data. So back in the days, for example, in this case, we had some false braking where we thought this car that's actually parked there was going to move into our path, and hence we were precautiously braking. But it is unnecessary because the car is truly parked. So how can we solve this? What we did was we mined the fleet for similar cases where the car had false braking due to some parked car. We added 14,000 videos to our training set. And then once we train the networks again with this new data, it now correctly understands that, OK, there is no driver in this car, hence it must be parked, so then there is no need to brake. And this is a systematic way to solve problems. On the chart on the right side, you can see that every time we add data, the performance improves. And then we can do this for every kind of task that we have in our system. And this is what we call as data engine. We identify challenging cases, such as the one you saw earlier. And there could be other different types of challenging cases too. We mine the fleet for such data, put it through our auto-labeling system, and produce the labels, add it to the training set. And once you have the newly trained models, we deploy them to the fleet. If we rinse and repeat this process, everything gets better and better. The final critical piece is the compute. In order to train these large models in a reasonable amount of time, you need lots of compute. In addition, compute is also required to produce the labels automatically. This is just compute in our data centers. In addition, we also have high computers in the car, which can run up to like 150 teraops of compute. On the back end, we have a 14,000 GPU cluster, and roughly 30% is used for auto labeling, and the remaining 70% is used for training. We also have a 30 petabyte of video cache, and this is growing to 200 petabytes. All of this is going to significantly increase once we bring Dojo, which is our training computer, on board into this. Just to give a reference, just the occupancy networks that you saw earlier use 1.4 billion frames to train these networks. We have already shipped our FSD beta software to pretty much everyone that has bought it in United States and Canada. This amounts to roughly 400,000 customers who can turn it on anywhere, and then the car would attempt to drive to the destination. It's still supervised, but it can already handle turns, stop at traffic lights, yield with other objects, and generally get to the destination. We have observed that people who use FSD are already 5 to 6x safer than the US national average. Like I mentioned earlier, the solution to scalable FSD is getting the AI architecture, the data, and the compute just right. And we have assembled a world-class team to execute on this. We are pushing the frontier on these three items, and as we improve the safety, the reliability, and the comfort of our system, we can then unlock driverless operations, which then makes the car be used way more than what it is used right now. With that, I'd like to introduce Elon back on stage to give some more updates. Yeah, this next slide is video.
It's kind of weird seeing the arms and legs just separate. We have a whole lab full of arms and legs. Worth bearing in mind that when we did AI Day, this version of Optimus didn't walk at all. So the rate of improvement here, I think, is quite significant. It's obviously not doing parkour, but it is walking around, and we have multiple copies, I suppose, of Optimus. The thing that I think Tesla brings to the table that others don't have is that we have the real-world AI. We're the most advanced in real-world AI. So the same AI that drives the car, which you can think of the car really as a robot on wheels, and this is a robot on legs. So as we solve real-world AI, and I don't think there's anyone even close to Tesla on solving real-world AI. That same computer and software goes into Optimus. So it's not that helpful to have a humanoid robot if you have to program every individual action. It needs to be able to walk around autonomously and solve tasks. You should be able to instruct it in simple things by showing visually what the robot needs to do, or just telling it what to do. So I think that's a key advantage that we have. And then we also are good at designing things for manufacturing and then manufacturing itself. So the actuators in Optimus are all custom designed Tesla actuators. So we designed the electric motor, the gearbox, the power electronics, obviously the battery pack, and everything else that goes into Optimus. We were quite surprised to find how little was available off the shelf. Because there's a vast number of electric motors, gearboxes and whatnot, that are available in the world. And we found none of them were useful in a humanoid robot, literally none. So you have to custom design the actuators for a humanoid robot. And so the same team that designed the groundbreaking electric motors that are in, say, the Model S Plaid, designed the actuators in the robot. So, I mean, for practical purposes, what this means is that we should be able to bring an actual product to market at scale that is useful far faster than anyone else. And assuming that the things I'm saying are true, or at least you can put it, I think they are true. It's just a question of the timing. You start getting into interesting questions of like, what's the ratio of humans to humanoid robots? I think it might be greater than 1-to-1. Because you could sort of see a home use for robots, certainly industrial uses for robots, humanoid robots. I think we might exceed a 1-to-1 ratio of humanoid robots to humans. It's not even clear what an economy means at that point. Since an economy is output per person times persons, but if output is much higher and there's no limit on persons, then what's the actual limit on the economy? We're still pretty far from Kardashev scales here, but we're getting there. So anyway, it's probably the least understood or appreciated part of what we're doing at Tesla, but will probably be worth significantly more than the car side of things long term. So charging.
I think Rebecca's next for talking about charging.
Charge.
Thanks. Hi there. My name is Rebecca Tinucci, and I lead our charging infrastructure teams here at Tesla. And at Tesla Charging, we have understood since day one that a great charging experience is the linchpin to electric vehicle adoption. And that understanding has meant that we've always taken a holistic approach to charging. That's a word that you've heard a lot here today, but what it means for charging is that we've considered every use case. We think a lot about what it means to charge at home, even if that home is an apartment or condo. And we spend a lot of time thinking about what does it mean to charge away from home, including if that's for daily commuting or if you're going on a road trip. And this holistic approach has led to some pretty incredible results. In 2022, we provided 9 terawatt hours of charging across our various charging methods. Over 50% of that was supplied via convenient AC home charging. And when our customers are away from home, they can visit one of our 80,000 charging points. That includes 40,000 of our beloved Superchargers. Now, getting here has meant that we've spent 10 years building charging infrastructure when basically no one else in the industry would do it. And while we certainly have a lot of areas that we want to improve, those 10 years have afforded us the opportunity to get pretty good at charging. First, we have the industry's lowest deployment costs. Our costs are often 20%, if not 70% lower than alternatives, and that goes for both our supercharging hardware and deployments and our AC charging product lines. A lot of reasons that we're able to achieve this, you've heard a lot of them here today. We're vertically integrated. We manufacture and engineer all of our own charging equipment. We share components across our different product lines. And on the supercharger side, we also install and operate all of our own sites. And that's led us to be pretty obsessed with finding new ways to innovate around installation. As an example, we have recently extended our excellence in manufacturing to how we build supercharger sites. We are pre-building 4-post supercharger units at our factory in New York. We load them on a truck, we truck them to site, and then we crane them into position. This method saves us 15% on our deployment costs, and we can install a site in a matter of days. Once we install a site, we also operate it really efficiently. Over the last few years, we've been able to cut our per kilowatt hour cost by 40%. Again, a lot of reasons for this, but one at the top of the list is we've focused on increasing our site utilization. Site utilization is just how many sessions or kilowatt hours can we push through a site or a post. And basically doing that allows us to spread our cost over more sessions, thus lower cost per kilowatt hour. But of course, that's easier said than done, because when we push up site efficiency, of course, the risk is that we have a poor customer experience and we have wait time at our sites. This is where Trip Planner comes in. Trip Planner is our in-vehicle routing or navigation system. Other electric vehicle manufacturers, well, some of them have vehicle-side data. Other infrastructure providers have site data, but at Tesla, we have both. And what that allows us to do is to use Trip Planner to route vehicles towards available sites and away from congested sites so we can balance our utilization without risking wait time. And the results speak for themselves. Over the last few years, we've been able to drive up site utilization by 30%. That means lower per kilowatt hour cost, while also cutting our wait time in half. And we think this can get even better. Today, we're feeding Trip Planner with real-time site information and information about vehicles currently at sites. Going forward, we'll be moving that to projecting site occupancy based on the understanding of what vehicles are currently routing to those sites. And ultimately, our vision for Trip Planner is that it's the air traffic controller for electric vehicle charging across all infrastructure on a global basis. And the last thing we focused on to get here is quicker charge times. We're really proud of what we've been able to accomplish here. We've shaved off 30% of our charge time, average supercharging site time, visit time, over the last few years. This has taken improvements on the hardware side, with our software, on our vehicles, and on our infrastructure, and we're really excited to continue pushing this trend down. Looking forward, the job does not get any easier. As you heard earlier, we aspire to a fully electrified global fleet. That fleet, from an industry standpoint, needs 9 petawatt hours of charging on an annual basis. And while Tesla charging certainly doesn't have to supply all of that, it does require that, for our part, we have a few new focuses in order to scale. First, if you want a fully electrified global fleet, all of those vehicles have to have a great and reliable charging experience. So, as many of you know, recently we have started opening up our networks on a global basis. Over 50% of our superchargers in Europe are currently open to other electric vehicles. We've also opened up in Asia Pacific with our first sites in Australia. And just yesterday, we opened our first 10 supercharger sites here in North America and the US to other electric vehicles. We've also invested a lot to be able to make this a really easy experience for our new customers. All you have to do is sign into our Tesla app to unlock a post and start charging. We've also, on physical site changes, we've also added hardware to our sites. They're called Magic Docks. And basically, that is installed in areas where we have different charging standards, and they allow for other electric vehicles to come to our site without having to bring their own adapters or hardware. We've also just started installing our 4th generation supercharger posts. Those are being installed in Europe first. And while it's not a big mention, not a big thing to mention, they do have longer charging cables so that we can more easily reach the charge ports of different vehicles. The second thing we need to make sure we do when we talk about scaling all of this charging infrastructure is we need to make sure that it's powered from renewable sources. We're very proud that over the last 2 years, we've procured enough renewable energy to offset the amount of charging we've provided to customers. But as we look forward and we talk about this fully electrified fleet on a global basis, we really want to make sure that the demand for charging more closely follows when renewable sources are available. Now, this chart is on an aggregate basis for the US, and it varies based on what your renewable generation sources are locally. But basically, what this shows is we want to kind of move that charging curve, and for solar and wind in this example, it means more daytime charging. And we think the best way to go towards daytime charging is to install AC charging that is convenient and low cost everywhere vehicles are typically parked throughout the day. So that's really the plan. While supercharging and home charging definitely stay a big part of the puzzle, our teams are currently scaling to install AC charging everywhere vehicles charge during the day so we can power them from renewable sources. So summing it up, while we've spent 10 years installing infrastructure that is low cost, it's efficient, and it provides a great customer experience, we're really just getting started when we talk about supporting Master Plan Part 3. We've got to scale capacity on an industry-wide basis to 9 petawatt hours on an annual basis. We've got to open up to non-Teslas and make the charging experience for everybody really great, and we've got to power all of this via renewable sources. And one more thing, yes, we've got to scale our infrastructure, and yes, we want to power it via renewable sources, but we're Tesla, so we also want to make sure that we're continuing to focus on providing really incredible charging experiences. With that, I want to welcome up our leaders of supply chain, Roshan and Karn, to talk a little bit about that topic.
Thanks, Rebecca. Hi, my name is Karn, and my team leads supply chain for electronics, powertrain, and battery at Tesla. And we've also got responsibility for indirect purchasing, construction procurement, and warehousing and distribution.
Hi, my name is Roshan. I've been with Tesla for over 14 years. My team manages vehicle commodities, solar, logistics, planning, and capital equipment.
10 years, forgot that. So today we wanted to provide you a quick overview of Tesla's supply chain and what really separates us from the typical automotive supply chain. As you've seen in presentations prior from Pete and Drew and some others, Tesla designs a lot of the subcomponents that go into our vehicles. So we're not buying things that are off the shelf from suppliers. So supply chain is not purely a commercial relationship as it is in most other companies. We actually have an arm within supply chain called Supply Industrialization Engineering. And the burden of taking a drawing, a design from concept and turning it into thousands of products produced at the right cost and at the right yield falls with this group. Of course, they work very closely with design engineering, but really the level of detail that our engineers get involved in terms of building the capability of the suppliers is pretty detailed. So, you know, once we get a new part, naturally with electric vehicles, a lot of the supply chain doesn't exist. Our engineers would basically take the drawing, turn it into a manufacturing concept, do the equipment selection, and physically go to the supplier and stay there for weeks or months, however long it takes, to basically do the line bring up. Once the line is brought up and we're hitting the right rate, the right quality, at the right yield, then we work on things like automation and yield improvement and those types of activities. So there's a big group of mechanical, electrical, industrial, you name it, engineers within supply chain, and it's their responsibility to take care of this. Now, this is a huge strategic advantage because we manage every detail of our supply chain, because we're so integrated with our partners that we know about issues before they happen. It's almost live. We've got dashboards, we've got connections, and across the 10,000 or so factories across the world that are making our components, we have a pretty good view of the health of those suppliers, and this has been a key asset in how we've been able to kind of manage things through a lot of different issues over the past couple of years. So, you know, supply chain is a game of perfection. Perfection is a passing grade. It's like you know, if one part doesn't show up, that line goes down, and our CEO finds out about it in less than 20 minutes. Tesla is very different than Apple. They outsource manufacturing, we do it in-house. So supply chain is kind of right in the middle. And perfection is increasingly elusive and very expensive if you kind of look at all the issues we've had to encounter over the past year. And today we're just going to talk about how we got through the past, and then what are we going to do going forward, and how are we going to get there. So let me draw your attention to this slide. On the left, you'll see a portfolio, our existing portfolio of products. Right at the top, you've got the S and X platform. In the middle, you've got the 3 and Y. I think everyone's more than familiar with those. And then the Tesla Energy platform, which is a very high rate of growth for us. And
don't forget the solar and superchargers.
And solar and supercharger. Thank you, Roshan. And you'll see a reduction in and then we basically got the tier 1 and tier 2 parts. This might be boring, but a tier 1 supplier is any supplier that builds and supplies parts directly for consumption in our 5 factories. And our tier 2 supplier basically does the same thing for a tier 1 supplier. So they are the supplier to our supplier. And depending on the supply chain of any one of these products, this can actually go down to the tier 6 level. So for example, if you're talking about the battery cell, we really get involved with the mines of like where we're procuring the lithium, the cobalt, and all that sort of stuff because we're procuring such high volumes of it. So you'll see a reduction in the number of parts on the SNX platform to the 3-in-Y platform. And this is because of the great work our design engineers have done of making the car simpler and easier to manufacture. In parallel, we actually had a similar strategy in supply chain. We had cast a wide net to a lot of suppliers for the SNX platform. There was a lot of suppliers that we invited to partner with us. And we used that platform as sort of a filter to see which suppliers have the technical, financial, and cultural capabilities to match us, right? Who do we invite to the party when we really scale things up? And we really dramatically reduced the number of suppliers that we were dealing with for the 3-in-Y platform, and this is an approach we'll continue to do for future platforms as they come along that are even more high volume. So this has really been our approach. It's made things a lot easier, and we could figure out the suppliers that were capable of moving at our pace, and then the ones that didn't have the desire to or the capability to. You need both desire and capability. Secondly, the complexity on the tier 2 level is very high, right? These are the suppliers to our suppliers, and there are a lot of components. So think about silicon, think about resistors, capacitors, diodes, all the little assemblies.
All the raw materials.
Raw materials, that's even further down.
Yeah.
But all these little sub-assemblies that have to come into Tesla, the complexity is immense. So even though at the tier 1 level we're talking about 8,000 parts total, it seems like a lot, but it's not a lot. The management of the tier 2 is really where we excel. And I'd like to illustrate that with an example. Meet the car computer. Very innocent sounding name, and it's anything but. This is an absolute monster. So I think you've all seen the picture on the left of the autopilot board. That's the top of the autopilot board. The autopilot board also has a bottom, and the bottom is populated heavily with components. On the other side of the heatsink, you've got the MCU, the multimedia cluster board. This board is equally complex. It's also double-sided, 8-layered. And these boards, these computers run so hot at peak operation that they have to be liquid-cooled through a heatsink. So this assembly requires taking those 2 boards and then bonding them to a heatsink that's hermetically sealed as an assembly, of course, flashing the software and all that sort of stuff. And then that's one part number that comes to Tesla. So this is an example of one tier 1 part number. That's a very complex assembly to manage at the tier 2 level. And there's more than 7,000 components here. There's as we stand here, a component's being assembled onto a car computer every 1.4 milliseconds. The line that builds this computer is the length of a football field. So it's quite complicated. And initially, when we first started building this board, due to the complexity of it, we had to rely heavily on labor. But once we dialed in the quality, the rates, and the yield, we started focusing on making this more efficient. The only way to control cost is by removing labor. The first step is removing labor. The second step is fully automating. The third step is turning off the lights and letting the factory run, ideally. And that's going to be the goal for us here. So 95%, but our work is not done. We're going to be going a lot further than this. So this illustrates the point that a part is not a part. A part has a lot of complexity underneath it. Supply chain is a game of multiple tiers. And what's made us successful is our involvement in all the details with our supply engineers that are Tesla employees. They're Tesla supply engineers. So they're like on our payroll that go and ramp up these capabilities that are suppliers. And then just managing each and every attribute of it. 7,000 a day through the chip shortage, through the pandemic, through all the other stuff that we had to deal with, was very difficult to manage. But because we had all the details, we were able to pull this off. Of course, supply chain is not just about parts. It's also about logistics and a lot of other things. So I'll hand it off to Roshan for sharing some stats.
Yeah, so talking about inbound complexity, just over the course of just last year, we moved about 16 million pallets from our suppliers to our factories. Just to visualize that, if you put those pallets side by side, it could cover the half the circumference of the Earth. And talking about, again, the tier 2 complexity, over 1 billion electronic components get moved every week to support the production that Karn and team manages.
This is right now, 1 billion components a week,
right.
52 billion a year. This is going to go up, by the way.
And on top of that, we also have the responsibility to make sure the right component is supplied to the right service location to support the growing fleet of our vehicles. And we have about 685 service centers that these components need to show up just in time. And then we've also been, as a result of pandemic and even before that, we're working on dual sourcing and triple sourcing some of our critical components. As a result of it, we have suppliers around 45 countries in the world.
Yeah, our approach really has been to bring the manufacturing of subcomponents closer to the point of consumption. It makes the supply chain more green because you're not burning diesel, moving stuff around. And it also gives us the security of supply of having multiple sources in case one factory gets taken offline.
And that's how we got through pandemic also.
Yep.
So last 3 years were incredibly hard. Karn and I used to look a lot younger pre-COVID. But on a serious note, pandemic really changed the game of supply chain management. We were just not being a regular supply chain person. We were rolling up our sleeves and negotiating with state governments, city managers, mayors to help kickstart our suppliers to restart their operations. You know, there are some really inspiring stories where our supply chain team really fought hard to make sure that the factories don't go down. And it's also a testament to the resilience of our supply partners. Having said that, you know, it was not all about resilience and never give up attitude. We had also laid the foundation of having dual sources, and also, you know, in many instances, we had many, you know, things that we had simplified, the parts that we had simplified, the supply chain design that we had simplified, due to which we were able to get through the pandemic in much better shape than rest of the automotive.
It forced us to adapt. You know,
Right.
we encountered issues one at a time. It was really a team effort. We heavily relied on the government relations team. You literally had to, the COVID pandemic, as you're aware, you know, happened in different countries at different times. But unfortunately, you need all the parts to make the car. So at any given point, there was one factory that was lying down. There was
Right.
one jurisdiction that was being, you know, that didn't want to. They wanted to shut down a factory because you had an outbreak. So learning the rules, understanding, coming up with argument points, leveraging the team, and getting those. It was a difficult but good experience.
Exactly.
We learned a lot.
Yeah, and as we were just figuring out to work with COVID, then the port congestion hit on the West Coast. Logistics lead time went up by, you know, twice the amount, and we were operating with less than 35% accuracy in the system. That means at any given point, the ETAs of the vessels were 75% off. So we figured out how to work with that, and then the chip shortage hits.
Yeah, the chip shortage. That was a nightmare. But we got through it. I mean, you know, I think it's a testament to the tenacity of the team and the resilience of our supplier partners. It's mostly behind us, and I think the results speak for themselves. Tesla was able to grow production volumes at a time where the rest of the industry had a hard time staying flat. I think they shrunk, actually, cumulatively. And you know, we're often asked the question, how do we manage through it? And the answer is very much kind of baked through the presentations today. First, we design our own electronics. So in order to control cost, we really had to go and build relationships with all the tier 2 suppliers to negotiate them directly. So these relationships were formed, you know, over 10 years ago, and we've really gotten to know them well. So when a shortage hit, we knew, you know, who to escalate to, who to call, who to ask for help, and really kind of swarming the issue at the point of constraint. So the best team, you know, strong relationships with vendors, and then we also have a pretty sophisticated capacity planning function. Tier 2 capacity needs to come on earlier than Tier 1 capacity. Tier 3 capacity has to be even earlier. And our team does a very good job of having that strategic alignment with all our partners to make sure that the capacity is ready before we need it. we're a mission-based company. Our goal is to put as many EVs out there. We did not let the pandemic phase us. We were full throttle. And it was pedal to the metal in terms of our demand signal. That also helped. The silicon industry has very long lead times. They invest billions of dollars in sophisticated fabs that take years to build. So that stability and demand is something they appreciated, and it's something that is very, very much a Tesla thing. So this was looking back, right? This is how we got here. This is how we got from 0 to 40,000 cars a week. Let's talk about how we get to 20 million. So the question gets asked, you know, is Tesla going to basically break the chip industry if we grow to 20 million vehicles? The answer is no. But let me walk you through a logic on that. So as it stands right now, a Tesla enabled with a full self-driving computer has 4 times the silicon content of a regular vehicle. So at about the 2 million run rate, we're consuming about 700,000 12-inch wafer equivalents. That's the industry term that's thrown around for capacity in silicon. That's how much we're using, so a little bit below 1 million. And the global wafer capacity, based on the estimates we've seen, is about 135 million. So we're about 0.5% off the industry. Not a lot. Now, if you get to 20 million, when we get to 20 million, and if we don't make any simplifications in terms of part count, which is also a separate work stream, I think Colin talked about it, Pete talked about it, we're not going to have all these different components. We're really going to simplify the architecture because simpler is better. But even if we don't do that, and we take the most pessimistic case, we're going to need 8 million wafers, okay? And the industry is going to scale to 200 million by that point. So still, we're less than 5% of the market share. And if we run the same offense we ran all along and continue to work with our partners and you know, invest in fabs and invest in capacity, we'll have the capacity ready by the time we need it. So I really don't see this as an impediment from a supply chain perspective to get to 20 million.
Now, I would like to talk about a page that we took out of the electronic playbook and applied it to the mechanical side. Our vehicles use currently the heat pump-based technology for the thermal system. But before heat pump, our vehicles used to have a dispersed thermal system connected by hoses. Engineering was inspired from circuit boards and then created a system which was extremely integrated, where 60% of the system was the size of a basketball, where it contained about 100 components, 50 sealing interfaces, and several different manufacturing processes, all were packaged into this tight size. Now, why are we talking about this? Well, we launched this system right during the outbreak of the pandemic in Model Y. The team was forced to manage 100+ components from different suppliers around the world remotely. So there are 4 videos playing at the same time. One is the video of the manual line that was created when we started the production. And this manual line produced a lot of quality issues, let alone throughput. So we quickly pivoted to a semi-automated line. But in spite of that, although the throughput was great, the quality issues sustained. So our team decided that fully automated is the only way to go. So before we automate the line, we created a 3D simulation. Now, not many companies or teams have this capability, where at this point, now when a part gets spec'd, we have the ability to create a 3D simulation of all the complex sub-assemblies that would be involved in making the part, and tell the suppliers exactly what equipment to purchase, what to test, and create an end-to-end line in simulation. And that's what we did here. So with the help of the simulation, we had a very detailed sub-assembly cell, which was juxtaposed with the supplier's factory layout. And then we, after a back and forth of iteration and optimizing the processes, we implemented this fully automated line in less than 8 months. And the results were remarkable. 99% reduction in labor force. So in a line that would need 1,000 associates to build the super manifold in full volume, now just takes 10 associates. And the quality also went up by an order of magnitude. We have a defect rate of less than 0.005%, and a super manifold rolls out every 7 seconds because we have created many automated lines. And these factories are the size of 2 football fields, by the way.
Roshan had to one-up me on that one. 99% 2 football fields.
So why are we talking about this? In a world where labor costs are increasing, labor participation is decreasing, there is a huge turnover, and the cost of implementing automation is going down by 3x in the next 10 years. This is how we are thinking about complex assemblies, and we are going to push this type of thinking into our supply base more and more, who will be building our complex assemblies. This is the only way we think we can confidently scale to the 20 million vehicles target. To summarize, we have laid the foundation in getting ready to execute Master Plan 3. Our strategy is supply chain design simplification. We are going to make sure that we have more control into the tiers of the supply chain. We are going to grow responsibly and sustainably with our long-term partners, and we'll automate.
Yeah, it's like, going from 0 to 40,000 cars a week was tough. I mean, it took a lot of trial and error. It took a lot of learning. There was a lot of pain. There's a lot of mental scar tissue, as Elon calls it, through that process. But now that we're at that level and the foundation is set, going from 40 to 400 is not gonna. It doesn't really faze us. We have a capable team. We've got capable external partners that have gone through hell with us. Our leadership team is galvanized behind the mission, and we're gonna get it done. So I'd like to thank you for your time and hand it off to Drew and Tom for the next presentation. Thank you.
Hi, everyone. My name is Tom Drew. I'm now responsible for global production and sales and delivery service. I joined the company back in 2014, and I've been running the company's business in Greater China and APAC. Today, I'm representing all the Gigafactories and talk about how we can make more cars and faster. So right now, we have 4 vehicle factories on 3 continents to serve our markets. The total number of manufacturing employees is over 65,000. This is also including our amazing team in Reno. They are making powertrains, battery packs, and drive unit for our vehicle factories. The total installed capacity in all these vehicle factories about 2 million cars a year. That said, we're always looking for opportunity to grow more capacity from the existing footprint. So you expect this number will grow over time. To build more factories is the start to building more cars, and we're certainly the expert of it. This is the before and after image showing you the progress we made back in 2019 when we built a Gigafactory in Shanghai. So in 9.5 months' time, we built a greenfield project to establish the vehicle factory. And 3 months later, we started to deliver our first customer vehicle. People always ask me, how Tesla can build a factory that fast. Really, we learned from our Fremont factory a lot. We talked to the survivor from the production hell and tried to avoid all the mistakes we made. We decided to design a straight line with the minimum number of up and downs and turns for easier manufacturability and easier construction. We also challenged all the assumptions that people ever know to build a vehicle factory. When we delete and simplified all the redundancies and the buffers, that's helped us to save a lot of time. Also, we have a very strong in-house construction team in Tesla. If there ever a job cannot be done by others better, and we bring this in-house. So we have this in-house construction team, have a full control over all the activities on site, from design, engineering to construction, site management. So this team didn't just build Giga Shanghai, they also built Giga Berlin, Giga Texas, and Giga Nevada. They're really the hero behind the scenes. Like Lars shared earlier, going forward with the new platform, the more modular design and densified Gigafactory will be able to make more cars from even a reduced.
It looks like this is going to go on for a while yet. What we're going to do is let the stream continue for those in the audience. Both Mark and I are going to resume this tomorrow, and we'll do our wrap-up at our normal Thursday morning podcast at 8:30 a.m. But the stream will keep going, so you can continue to watch the stream if you like.
The 4 millionth vehicle actually.
And we'll see you in the morning. Thank you for joining us.
Thanks for joining us. On our shop floor, you probably walked past it. All right. So it took us 12 years to build the first million vehicle, and about 18 months to build the second million. The third million took us 11 months, and just shortly, less than 7 months, we built the 4 million cars. So we're getting better and faster.
Exponential growth.
Really kudos to the team. So, what it takes to ramp a Gigafactory? Well, if you have 600 robots, 10,000 trained employees, or 5,000 human and 5,000 Optimus, and hundreds of processes, you can do it. Sounds simple, but it's extremely hard. So there's two key metrics that we predominantly focused on. It is the overall equipment effectiveness and the cycle time. In Tesla, we're setting the passing grade for our vehicle factories with 90% OEE and 45-second cycle time. What that means, the OEE really evaluates the equipment uptime, the machine performance, and the quality. Simply put, this is the actual production time on a good quality product versus the planned productive time. The higher, the better. 45-second cycle time, that means you expect every 45 seconds there's a car running off the final assembly line in the factory. And the faster we ramp, the faster we can get the economy of scale. If you look at the chart on the left, Shanghai be able to significantly drop our labor hours per car during the ramp. The little dip there has happened in the last Q2 2022 because of the COVID shutdown. And on the right is the Fremont Model Y shop. Even this is a 60-year-old facility, the team there still be able to optimize the material flow, eliminate all the single point of failure, and drive higher output, hence reduce the labor hours. And actually, this factory keeps setting a new record. Yesterday, they just had a new factory daily record.
Congrats, Fremont team.
Absolutely. So, how can we reduce the cycle time, keep improving efficiency? We follow the philosophy Elon shared about building rockets, which is questioning, basically find the right problem to solve, and we start with delete, simplify, then we try to accelerate, pressurize the line, and find if the solution actually work. And at last, we think about the automation. There's one example in Gigafactory Shanghai. In the paint shop, we find that there's a overlap baking range between the PVC sealer and the top coat. It was done by 2 different ovens, and we decided to combine the 2 processes. Eventually, that helped us, didn't just help us to reduce the cycle time, but also save the 9% of energy consumption and the 9% of the CO2 emission. Also, we commonized the SNX design in Fremont. Right now, we have a common body and common headlamp. We eliminated about 40 parts and reduced about 10% of the cycle time. So all these improvements really help us to get to a faster ramp trajectory. And we didn't just learn from these high-volume existing factories. We also learned from the new factories. Most recently, our Berlin factory team implemented a 5G private network on the shop floor, helped us to overcome about 90% of the overcycle issues for a particular process in GA shop. We're going to soon implement this globally. right now, we have an integrated global organization from production all the way to sales and delivery service. This will help us to strengthen feedback loop between manufacturing and the service. We obviously want to bring a delightful customer ownership experience to our car owners. With this direct feedback loop, we be able to turn customer escalations and the feedback into quick actions and improvement on the shop floor immediately. With that effort, in the past 6 months, we'll be able to reduce the time in service and early ownership service, also service appointment wait time significantly. So 4 factories, not enough. If we want to hit the 20 million car a year target, we're going to keep building new factories, new lines, and that will come up with new product as well. And with all Gigafactories now in one organization, we'll be able to replicate unified ideas across factories. Also, we will help the new factories that ramp faster and also produce a better quality at a lower cost. Now I'm going to hand over to Drew to talk about the cell manufacturing.
Thanks, Tom. Yeah, we're not just talking about new vehicle factories, but also new cell factories. And we're going to talk about how we follow the same model when we do so. But first, I thought I'd just provide a little bit of an update on cell production. So remember Battery Day, we showed this video with the spoon and how we went from dry powder to film. Let's just say there's no spoon now. So many of you in this room saw this on your tour today, but here is our dry electrode machine here in Texas, one of the lines we have installed here. Fully automated, no spoon, from powder and foil in to coated electrode out. From a peak productivity perspective, per tool perspective, this is over 20 times the productivity of the tools that we showed folks on the tour in Cato back in Battery Day. So we've made a lot of progress on one of the key parts of the cell manufacturing process. And we've also continued to focus on refining the way we make cells and the factories that the cells go inside. As you can see on this chart, from typical 2170 cylindrical cells to 4680, we made a huge leap, which is basically a 5x reduction in the factory footprint and volume and footprint. And then going from what we did in Fremont and our pilot line to Texas, we improved further, and we're improving again when we go into Nevada. And what this actually represents is a series of actions taken by a very integrated, holistic design team across the product design, the manufacturing design, the process design, the equipment design, and the facility design. They all need to work together to make this happen. And you can see on the bottom, just as an example of simplicity up, investment down, and scaling up. Parts, we've reduced the number of parts in the cell, the number of processes, significant reduction in the number of processes. And collaborating with those 5 design groups, we've been able to end up with a factory that's 10 times smaller volumetrically, which means it's faster to get built. It's much lower capex per gigawatt hour output, and we can go and scale, to our objectives of, 240 total terawatt hours, 1 terawatt hour a year of stationary storage and 20 million vehicles a year, with the scalability that is required to achieve our goals. And we're not just looking at the cell factory itself, but also upstream materials where necessary. What you see here is the rendering of the 50 gigawatt hour a year Corpus Christi lithium refinery that we've already broken ground on here in Texas. The facility will start commissioning by the end of 2023, this year. This is a good example of something where we're basically talking about breaking ground and starting commissioning within 10 months, and with actual production within 12 months. That's the target, similar to what we did in Shanghai. Again, the result of collaboration and internal execution of construction in partnership with local communities. This site is 30 minutes from the Corpus Christi port. It's located directly on rail. The process route we're taking is a direct soda ash leach of the input material, which means there's no acid roasting. We don't have any of the sort of waste products associated with an acid roasting step. We're designed to consume lithium spodumene, which is a very commonly traded lithium rock, but it is flexible to other feeds from primary and secondary sources. And similarly, we're working on our cathode facility here in Texas. Maybe you've seen it as you're driving around, which is a 60 gigawatt hour a year cathode facility behind the main building here. 10-month build time there as well. The equipment's being installed for the first line as we speak, and we'll be commissioning starting next quarter. So we are doing this where we need to. Our plan is not to do it always. There are lots of competent companies out there. But we are also trying to sort of accelerate the pace of the industry by trying some new things that are a little bit more scalable and de-risking certain innovations that improve productivity in terms of CapEx per gigawatt hour and things like that. And with that, I think that sums up our efforts on the factory side. Mike, you want to come up and we'll talk about energy?
All right.
All right. Take it away.
All right.
Here, you can.
Hello, everyone. My name is Mike Snyder. I lead our Megapack organization. I've been with Tesla for almost 9 years. I'm excited to talk to you today about the Megapack product and the business and some of the exciting things we have ahead of us. From the beginning with this business, we have always focused on building successful projects for our customers, and not just the batteries in the box. We've built a hardware and a software platform that is able to adapt to environments all over the world, and that is able to scale from small island projects to large gigawatt-hour scale batteries. We've invested our time and our talent to best understand every aspect, every step in the process, and every risk of a project to ultimately provide a solution that is thoughtful, intuitive, provides great value to our customers, and is as plug-and-play as possible. And yeah, just looking at these projects, it's incredible to see them all come together in one montage.
Seeing the future.
Yeah.
Compressed.
It's 10 years of building these projects, and it's incredible to see the impact and to see what we have in front of us.
Absolutely.
We're on our 6th generation of our industrial product, which is the Megapack XL that we're building out of Lathrop, California. We've deployed over 16 gigawatt hours of industrial and residential products across 50 countries. And really, Megapack is a market leader. It's best in class in efficiency, reliability, energy density, and easiest to install, lowest cost to install.
And we call it XL because it is actually the largest, heaviest object that you can transfer around the roads of the world without having to shut them down and get crazy permits and things like this. So it is extra large, and there is not going to be an XXL. Let's just say it that way.
There's been incredible demand for the product. 2023 is going to be a great year. We have gigawatt-hour scale projects being built. The Lathrop factory continues to scale and ramp up, and there's new products on the near-term roadmap, so a lot to look forward to. How did we get here? Number one, a maniacal focus on all aspects of delivering stationary storage. What do we mean by that? What are some examples? As you see here, the Megapack enclosure, for one example, we designed the wireways directly into the base of the enclosure. So typically you need to install a bunch of conduits and cables under the ground. Now you can lift them up and install them directly into the base, increasing the speed of deployment and lowering the cost. Next, we see the batteries and the power electronics. And the power electronics is really the beauty and the elegance of the Megapack. So this is what converts the DC power to AC power on the grid. The brain is built directly into the product. It is able to connect to any grid in the world right out of the box. It allows all the Megapacks on a given site to work as one unit. And really, it's what makes it what it is. I think it's the most incredible feature of the Megapack. As you build out the full site, what we end up with is the most energy-dense solution on the market, upwards of 300 megawatt hours per acre. And just as a frame of reference, this solution is 2 times more power dense than a typical gas peaker plant. So this is the future. This is where we're going.
This is the product that retires the fossil fuels.
Yep.
One power plant at a time.
We talk about power electronics a little bit more. Tesla is a leader in power electronics. We've deployed over 1.4 terawatts across energy storage and vehicle. And we deliver more power electronics than the solar and the wind industry combined on a per annum basis.
And power electronics, it's hard to overstate how impactful they are. They are really the glue in the sustainable energy economy between generation, storage, and the end use. You know, those power electronics devices are switching, you know, thousands of times per second, hundreds of thousands of times per second to efficiently react to whatever is needed, either in the car or in the grid. And because they are so like sort of software driven at their core, they can provide functionality that hasn't been available to the grid in the past. And it's one of the reasons why renewables and storage together are such a great solution.
Yeah. And one reason that we focus on power electronics and control so much is because of the impact that it has on the projects directly. So just as an example here on the left, we have a firmware feature that we call virtual machine mode. And what virtual machine mode is it contributes to grid stability like a car's shock absorber that dampens oscillations or vibrations and keeps the ride smooth. So you can imagine if you don't dampen those vibrations, the vehicle could lose control or someone could get hurt. On the grid, you could have a blackout. We have one grid operator that's utilizing virtual machine mode and said they will not operate their grid at 100% renewables unless they have this feature, unless they have virtual machine mode working.
Yeah, and
they tried and it didn't work very well.
And why is it virtual machine mode? It's like synthetic inertia, where you turn the battery power plant into, like through software, behaving like it's a giant spinning machine, literally, and that like inertia stabilizes the grid.
Right.
But you don't need a giant spinning machine. You don't need like a huge fossil fuel power plant or a giant hydro turbine. You can just have the battery do it, and you can program it to whatever you need at that part of the grid, or even have it be dynamically changing as the grid conditions change.
Right. And that's why we focus so much on it. We believe it's the future of how batteries are going to add value. It's going to be more about adding power stability, just as it is about energy.
Yep.
Yep. Autobidder is another software feature I wanted to mention. Autobidder is an autonomous energy trading platform that in its most basic sense is buying energy low and selling it high, and the owner can net the difference of that. But operating battery storage is actually very complex. Needing upwards of hundreds or even thousands of decisions every 5 minutes. It's much more complex than a solar plant or a wind plant or a thermal battery or thermal generation plant. And it's mostly because of the versatility and the ability of the battery to provide so much value in different ways that these decisions need to be made in real time in order to optimize and get the most value out of the battery as it can. So there wasn't a solution that existed in the market, so we built one ourselves. In the markets we've deployed them in Australia, in Texas, in the UK, it has proven to be a market leader. We're continuing to invest in Autobidder as we expand to new markets. Second point of how we got here, a relentless focus on speed of execution, and there's 2 points to be made here. First one is in building factories. What you're seeing here is a time lapse of the mega factory that was built in Lathrop. We took it from a JCPenney distribution center to a world-class manufacturing facility in less than 12 months, which is incredible. And really, the way that we did this is similar to what my colleagues have described. It's leveraging the vertical integration of Tesla. It's getting the vehicle manufacturing team in the same room as construction and engineering and making decisions quickly with all the stakeholders and decision makers. We're using the lessons learned from Lathrop as we speak, as we plan for our next factories. Second, it's about installing projects faster. I've mentioned this already, but plug and play is kind of at the core of what we're going for. Over the past 4 years, we've increased the installation speed by 4x, and we've reduced the total labor involved across both construction and manufacturing by 3x. We think that this is key to unlocking our ability to scale and our customers' ability to scale with us. We need to be laser focused on reducing that time from when the Megapack leaves the factory to when it is operational on the grid.
And it's not just about centralized storage, it's also about distributed storage, the future roadmap of well, at least here at Tesla. And maybe some of you know about this sort of retail plan we have here in Texas, and I just wanted to talk a little bit about how that all fits together. So Tesla Electric really unlocks the full value of distributed energy and storage products. So it enables our customers to become their own utility. The data on the page is from our South Australia virtual power plant, another Tesla Electric setup that we have. Over 2022, it's 5,000 customers that we have the data for. You can get a sense for what's happening. So just if they were being provided default utility service and you looked at the cost of serving them that electricity, on average, $140 a month. If they all had solar and Powerwall, but the solar and Powerwall wasn't interacting with the grid, wasn't participating in the energy market, the cost of serving that customer would go from $140 a month to $70 a month. If Tesla Electric is operating those assets in an intelligent way to benefit the grid, Tesla Electric being basically a software that we developed out of Autobidder for the purposes of these distributed energy resources, we can actually pay the customers to bring their energy services to the grid. That's what happened in Australia last year. And Australia is a little bit of a special case. They represent the future, South Australia in particular. Solar and wind supplied 70% of South Australia's energy in 2022. That compares to 30% in Texas and 35% in California. But this is an indication of where this is all headed, of both centralized and distributed storage resources providing the key to unlocking fully renewable grids. And Tesla Electric is the retail plan that we're using to bring that to bear for our customers that have our products. And this is how we're rolling it out. First, as it exists, it's available in Texas for people who have Powerwalls in their homes. But we need to extend beyond that. Over 1 billion people live in markets with competitive retail electricity. And there's over $2 trillion in annual energy spend in these markets. This is a huge opportunity. And our intention is to bring this to market by market in the same way that we've approached Tesla Insurance, where we can bring value to our customers to reduce their total cost of ownership of our products. So actually what we're going to do next, and this is pretty exciting here in Texas, by this summer, we're going to offer a retail electricity plan to people who have our cars where they can have unlimited overnight home charging for $30 a month. This is part of reducing the total cost of ownership of our vehicles. And the reason why we can do this is because Texas has a ton of wind. And in Texas, the wind blows at night. So actually serving these customers with electricity at night for their cars is the best thing to do for everyone. And so this is a way to incentivize people to charge at home at night directly from renewable power. It's part of the grand master plan we talked about at the beginning. So we're very excited about this. And we do see this, similar to Tesla Insurance, as I said, as further reducing the total cost of ownership of electric vehicles. So putting this all together, we're really at the beginning of this massive ramp in energy storage deployment. And
reflecting back on the master plan, we talk about needing tens of terawatt hours of stationary storage. So we have our sights set on annual production rates of 1 terawatt hour, which is 25x our capacity at Lathrop. In the near term, we see really strong demand for the Megapack product, over 100 gigawatt hours per year in 2023, and growing by over 100 gigawatt hours per year over the next few years. So the demand is there, and naturally, as we continue to focus on cost and speed and value, the things that we've mentioned, it's clear we need to build more capacity and we need to ramp it quickly. So while the challenge is big, it's also a huge opportunity for Tesla. It's a huge opportunity for the Megapack business. And I'm excited to see the impact that it's going to make on our grid transition.
As am I.
Yeah.
All right.
All right. Thank you.
Thank you all. Yes. All right. And Lori, Brandon, come on up.
Hi, I'm Brandon with the legal team. Thank you, not just for coming, but being investors. Now, we have an active and engaged board and management team. We've met with you, and today is the culmination of that. We've heard you, which is why we're excited to share this Investor Day with you. Now, you will hear more from our board at the appropriate time, but for now, I'm excited to introduce Lori Shelby, who's going to discuss sustainability and our employees. Lori?
Thank you, Brandon. Hi, everyone. My name is Lori Shelby, and I lead the Environmental Health, Safety, Security, and Sustainability team. I've been with Tesla for 5.5 years. So I'm going to talk about Tesla's impact. And of course, that starts with our awesome team members. So you've heard a lot today about our amazing products, our process, our software. You've seen lots of numbers and lots of graphs. you've also heard a common theme. And that common theme is that Tesla's team is what drives our success and makes a difference. Whether you're in our factories, in our sales, service, and delivery centers, our warehouses, or in the field, you can see and you can feel the collaboration that's happening. And you also can see the pride that everyone has in working for Tesla. So before I go on, I want to give a big shout out and a thank you for our Tesla team globally. So let's. That was great. That was great. Thank you. So we are creating a lot of meaningful work through our jobs. We're a huge employer, and we're growing every day. We're at 129K. And more than half of our team works in vehicle manufacturing. And almost 60% of our team is based in the US. People want to join our mission. And we need to grow, and we need to hire the best people. Engineers want to work for Tesla. Look at number 1 and number 2, SpaceX and Tesla. In 2021, we got 3 million applicants. 3 million. That's incredible. And our culture at Tesla is anyone at any time can raise an idea or make an improvement suggestion across safety, people, cost, production, quality. Because we have a very simple process called Take Charge. And Take Charge is really employee engagement. And as Take Charges go up, as you can see in this graph, injuries go down. And you know why? People who do the work, the people who do the work know how to improve the work. Sustainability is everything. It's our mission. You've heard about it all day, part of our master plan. But at Tesla, we don't just tick boxes to meet a requirement. We really focus on the impact that our products and our software will deliver. In 2021, our customers avoided 8.4 million metric tons of greenhouse gas. That's equivalent to taking 1.7 million ICE vehicles off the road for a full year. Yes, yes. We're also focusing on doing really good work and driving sustainability into our operations. We have year-over-year reduction in our water use, in our waste, and we're growing and building a renewable energy program within our operations, just like supercharging, as you heard. So it's not just about our products, it's the way we make our products, both phases. Tesla, our company, is solving both sides of the clean energy equation. We've got the clean generation, the clean storage. We also have zero emission transport. As this slide shows, from 2012 to 2021, our products generated more energy that was consumed by all Tesla vehicles and our factories. It's amazing. Yeah, I like the claps. Yeah, I'll take claps. So our vehicles use less emissions than gas-powered vehicles. Even in the worst case scenario, 100% coal grid, the Model 3 has less emissions than the average ICE car. And we're only gonna get better. You heard about that today. Every product we make is more efficient. Every factory we build is more sustainable. So it's only gonna get better and better. So as we build our zero emission future, we've been talking with our stakeholders, with our shareholders, about how do we improve our reporting framework. And we are aligning with the TCDF, So TCFD. So we're aligning with the TCFD, which I know many of you have been asking us about. I also want you to stay tuned because there's going to be much more coming in our impact report. So thank you all. And up next is Zach Kirkhorn.
Thank you, Lori. All right, so this is our last section of our prepared remarks today. We'll kind of take what we've discussed today and summarize it at the corporate level for our financials. Maybe before I jump into the details here, we've never done an investor day as a company. We've never brought our leadership team out and asked them to talk about the things that they're working on. So, I feel very fortunate to be able to work alongside this group of people and support their teams. And I also just want to thank them, they're in a room in the back listening to this, for all of the work that they put into today and getting the company to where it is today. So thank you to the Tesla team. When we were preparing for today, folks were asking, well, Zach, what should we talk about? And really the only guidance we gave folks is, well, talk about the things that you're working on and talk about it in the context of the master plan. And what did almost everybody talk about today in great detail? All of the work that they're doing to take cost out. Because in this industry, in this business, you survive or you die based upon the ability to manage your costs. And so I'd like to talk about cost as well. If we look at our longest running scale production product, this is the Model 3. We reached 5,000 cars per week, which was our design capacity in mid-2018. And since then, we've taken 30% of cost out of this product. And there's 2 points I want to make about this. The first is that cost reduction, as you have heard throughout the course of the day, is deeply ingrained in our culture. And I think one of the most important reasons why we are here today as a company. The second point that I want to make is that when we're working on cost reduction, it's easy just to take cost out and make our products worse. But we have to take cost out and improve our products at the same time. This is the hard thing to do, but it's the necessary thing to do to continue to move forward. And if you look at a version of a Model 3 that we built today, and you compare it back to a Model 3 that we built in 2018, there's a long list of improvements that we put into the car while also taking cost out of the product. Cost reduction doesn't just come from one place. There's no silver bullet here. And we pushed the boundaries on volume with the Model 3 program, increasing volume 3x over this period of time. We've improved productivity. So in our Fremont factory, we are twice as productive now as we were in mid-2018. We've made a lot of progress on overhead efficiencies and product improvements, as we've discussed, and a long list of other things, including localization, our factory in Shanghai. And as we ramp up volume and as we find efficiencies, we work with our suppliers to do the same. And that leads to material cost reductions that improve the affordability of our products. And as we look forward to our next-gen vehicle, our target is to reduce 50% of cost, and we've talked about that a bit earlier today. Going from the Model S and X platform to the 3 and Y platform, we took out 50% of cost, so the task here is to do it again. And this is very important because as we improve affordability, the number of customers who have access to our products dramatically increases. And as we link this back to our master plan, it enables an exponential growth in our volume with linear reductions in the cost of our products. The second point I'll make here is that, and again, cost reductions don't come from any single one place. And so you can see the buckets here on the vehicle side, battery and powertrain, manufacturing cost reductions, and others. These buckets are relatively equal in size. And so in order to take 50% of cost out of the product, we have to go through everything. But more importantly than just the cost of the car up front, when we're transitioning to a sustainable economy, particularly with vehicle ownership, it's really important to think about the lifetime cost of the products. And this chart here is showing what the total cost of ownership per mile is over the course of 5 years. And we have to think about financing costs, insurance costs, the cost of power. Drew talked a little bit about that with the plants that we're doing in Texas, wear and tear and maintenance on the cars, et cetera. And we're already at a place today in the US where a base Model 3 on a cost per mile basis is less than a Toyota Corolla, which is the highest selling car in the world. And as we move towards our next-gen platform, we will continue to reduce this. And as we work on robotaxi variants of this platform, this cost will come down even further. And so this is a product that we expect to have substantially lower cost per mile than the highest volume products in the world. The next thing on cost reduction I want to talk about is operating expenses. We spend a lot of time on our earnings calls talking about gross margins and product cost. We don't spend a lot of time talking about OpEx, but I think this is one of the really important parts of our story. So since 2018, we've reduced our non-GAAP OpEx 60% as a percent of revenue and 75% on a per delivered car basis. This is quite staggering, and I want to go into the details about how we've done this. The first component of OpEx, which is R&D, the single most important thing here is that we constrain the number of programs that we work on, so minimizing the number of programs that we're running in parallel. And the key here is to maximize the revenue and cash generated from every program that we work on, and also maximize the technology sharing between the programs. So we talked a little bit about how power electronics in our energy business is shared with power electronics in our vehicle business. If we look at the SG&A side of this, I think the story here is pretty dramatic. So we're showing here a comparison of SG&A per car delivered compared to the traditional auto industry, which is both an OEM and the dealership network. And our estimates are that we're 60 to 70% lower on a per car basis. And if you turn this into dollars, this is many thousands of dollars per car. This is part of the reason why on the last earnings call, I made the comment that we think about operating margin more so than gross margin as a company, because the integration that we have here on the SG&A side, particularly with vertical integration into our dealership network, this provides efficiencies that give us a competitive advantage from a cost structure standpoint relative to other companies. The other thing that I'll note here is that this wasn't always the case. And it wasn't that long ago where these bars would be inverted. And if we go back a little bit in time, and we talk about when we launched Model 3 in the Fremont factory, we went from 2,000 cars per week, which was S and X, adding 5,000 a week to that for Model 3 got us to 7,000 cars a week. You've heard some folks here today talk about production hell. What I don't think we've ever talked about as a company is back office operations hell, which also happened at the same time. And 7,000 cars a week, 350,000 cars a year, we want to go to 20 million cars a year, and we're struggling at 7,000. And we're saying to ourselves, we have to completely rethink the way that we're managing our back office operations if we have any hope of efficiently scaling this company. And so this began a process that we're still continuing to work on today, but it's something that we refer to as the Tesla operating system. So in the same way that we're vertically integrated into the software that manages our cars, we've also vertically integrated into the software that runs our company. And all of our major departments in the company are using, not all of them yet, but almost all of them are using our in-house software. Most recently, we removed third-party recruiting software, and we're now running our own recruiting software as a company. And this matters a lot because rather than having a complex web of third-party systems that are generic solutions that take a lot of effort to customize for our particular needs, we've been able to put in place with an in-house applications engineering team dedicated, lightweight software that does only what we need it to do and nothing more. And that team works very closely with process improvement teams that sit within the business, who are looking through all of the processes that we're managing as a company and following the exact same process that Tom mentioned in the manufacturing space to look at our processes, delete process steps that we don't need, simplify process steps that are existing, and automate what's remaining. And the results of this have been quite staggering, to be frank. I think it's exceeded our expectations as well. On the left side of this chart are some examples of the efficiency improvements that we've seen within our SG&A areas as a result of this strategy. The North American sales team is 4 times more efficient now than they were in 2018. Order operations team, financial services. I mean, these levels of improvement are large, and there's not enough pixels on the slide here to list out everything, so it's just a couple of examples. And then in the same way that when we look to take cost out of our products, we want to feature up the product or improve the product while taking cost out, the same has been true with the use of Tesla operating system and that integration with our process improvement teams within the company. And so we've increased performance and added capabilities while also dramatically reducing cost on a per car basis. There's a list of self-service functionality that we've put in place, which customers like. It also simplifies our operations behind the scenes. We've used the Tesla operating system to expand into our captive insurance space, which we are fully vertically integrated into. We run our own in-house software. We have our own agents, our own claims software, and claims folks who run our insurance business. This is also very important because as a technology company, data is very important. And we use these systems and the access to the data in those systems to pull out extremely granular and targeted reporting that enables us to see every aspect of our business in real time so we can make adjustments to our operations as needed. And there are sometimes examples where we say, man, I wish we were tracking this piece of data. Well, you know, it's a team's meeting away from the applications engineering team to make a request, and then we can start tracking that data and make those changes. And so the feedback loop associated with process improvement inside the company is pretty astounding. The last thing I'll just mention here, which is something I'm personally quite proud of, we've made a lot of progress in our close processes within the finance team, getting our 10Q and 10K filed. It's amongst the fastest of the 20 largest market cap companies, so great work to the finance team here. So all of this work on cost reduction is extremely important because we have a lot of money to spend ahead of us to achieve our goals within the master plan. So we've mentioned over the course of the day today 20 million annual vehicle production as our target, 1 terawatt hour of annual energy storage production, and then expanding cell production, service, and charging in line with the growth of those other businesses. And so we've estimated what we think the total cost to get there will be, and there's certainly error bars around these numbers as we continue to progress and innovate. But of this, we've spent about $28 billion of that so far in the history of the company. And maybe this total investment looks large. I actually think it's quite small relative to our ambitions. And if you look at our 2022 operating cash flows and you just say, well, let's assume some modest growth to that, maybe not all that much, if you're being conservative, but the ability to pay for this level of investment from the forecast that we have is very achievable for us. I'm often asked about capital allocation. I think our strategy here is very straightforward. I touched upon it a little bit in our last slide, but just to be explicit about it, obviously the priority here is to ensure that we're using capital to run the day-to-day operations of the business. This is a working capital intensive business, and this has to be managed very carefully. And so, you know, over the course of a quarter, there can be multi-billion-dollar swings in our cash balance up and down, just depending upon the timing of when we build and deliver cars. So we obviously have to have money set aside for that. Downside protection is another really important area where we have money set aside for that. And over the last couple of years, throughout the pandemic, I think this just highlights why being ready for downside protection is important. Preserving daily operations is the engine that then generates cash that allows us to reinvest into the growth of the business. And I'm very proud that over the last couple of years, despite the ups and downs in the macro environment and interruptions to supply chains, we have never once pulled back on our investments in growth, so that remains a huge priority for us. We do then, after investing in growth, we look at opportunistic ways to spend our cash. These are more financially oriented, where if a return exceeds a hurdle, then we can place cash in that. This is part of our story of cost reduction in the Fremont factory. And then on the excess side, you know, this is where, you know, the board meets on a regular basis and they're thinking about what our cash flow projections are looking forward and whether it makes sense to do buybacks or dividends. So to wrap up the finance portion of the presentation today, a couple of key messages I just want to leave you all with here is that we use innovation at an intense level to drive costs down and improve the efficiency of the business. And the reason this is so important is it allows us to improve product affordability. And this is particularly the case when we move to our next generation platform. Improving affordability allows us to comfortably make investments that grow volume. That volume generates cash that then allows us to make more investments. And as we integrate that going forward, it's our belief as a leadership team here at Tesla that we're going to achieve unprecedented scale in the manufacturing space. And this is what's ultimately required to accelerate the world's transition to sustainable energy. So with that, this completes the prepared portion of today. We're going to take a short break, and then we'll resume with a live Q&A. Thank you all very much.